Assalamu alaikum. Good morning, everyone. I hope you enjoyed yesterday, first day of the symposium. And we are up to a second day, an exciting second day, inshallah. We have an agenda, full day agenda, with many speakers from academia and from industry as well. So without further ado, please join me to welcome on the stage Professor Jacob Dunningham from Sussex University for the first keynote speech for today.
Thank you. Microphone, can I grab one of these?
Yeah, absolutely.
Right, well, good morning, everyone. Thank you for coming out bright and early. You might hear my voice is a little bit croaky. I'm sorry about that. It disappeared last night. We were having a wonderful evening with dinner, and as the evening went on, my voice faded and faded. And it's trying to escape me, but I think I'm going to hang on to it just long enough for the talk. But please excuse the slight croakiness of it all. So I'd like to thank the organisers for what I think has been an absolutely wonderful symposium. I really enjoyed yesterday. There were some fantastic talks. I had some great conversations with people, and I'm looking forward to having more of those again today. So thank you to all of you for engaging, and thank you to the organisers for the wonderful opportunity. So my name is Jacob Dunningham. I'm at the University of Sussex in the UK, and I work on a number of different quantum technologies as a theorist. But the thing that has really been a mark of my career over the last, well, probably decade or more, has been quantum metrology, quantum sensing, and quantum networks. And that's what I want to talk about today. So a number of people have asked me where the University of Sussex is, so I thought I'd put a slide in. So we're located down on the south coast of England, just south of London, about an hour south of London. And this is our campus here. We're lucky to be within a national park, actually. It's the South Downs National Park. It's really beautiful countryside. You'll notice it's very green, and it's very green because it rains a lot. And I was going to apologize for bringing the rain with me to Saudi Arabia, but everyone I've spoken to has been very pleased to have the rain, so I'm happy to take the credit instead. Anyway, this is the campus. We're just like here, we're near the coast, so there are lovely coastal walks and beaches, and it's a nice place to visit, and all of you would be very welcome anytime to come and see us. So within this university, we have a very successful Centre for Quantum Technologies. There's about 80 researchers working within this. There are 9 faculty working in 7 different core quantum technology groups. And I think one of the marks of this centre is the breadth of what we do. So we do everything from quantum computing, that we've been hearing a lot about today, to quantum simulation, quantum clocks, quantum imaging, quantum metrology, quantum communications. So we really cover a very broad remit of quantum technologies, which I think is really nice. It means if ever I've got a question about anything, I know I can find a really good expert on hand. So I thought I'd just say a couple of words about why I got interested in quantum metrology and quantum sensing, because this is a little bit of a deviation from the main theme of this symposium, which has been about quantum computing. So I look back, this was one of my very first papers actually. It was when I was doing my PhD, and it was a time when Bose-Einstein condensation had recently been realized in dilute gases, and people were very excited about this, and experiments were going forward very quickly. Theory was being developed, and I worked with my supervisor, Keith Burnett, on playing around with some of the theory. And one of the things people were worried about at the time was the fact that atoms interact with one another. So there's this nonlinearity, and people tried to get rid of that because it complicated the theory and messed up some of the applications people wanted. But I think it's a good principle to take, to not try and fight nature, but to work with it. So we thought about how we could use these nonlinearities to help us. And you know, they give rise to squeezing, they give rise to entanglement. And so we developed this nonlinear interferometer, where the nonlinearity naturally comes from the interactions between the atoms, and thought about how we could use this as a way of achieving metrology below the standard quantum limit. And I was very pleased that a few years later, Marcus Oberthaler's group in Heidelberg did this experiment, and they were able to show quite nicely that this does work. So these grey bands here are the standard quantum limit. If you can tune the interactions and turn them off. If you do that, you get these blue bands, so slightly less good than the standard quantum limit. But if you turn these interactions back on, then we get these red bands and you do a bit better. So the improvement is not huge, but it was a first proof of principle that you could do quantum-enhanced metrology with atoms. And I have to say I kind of got hooked then, because it was this nice interplay between theory, seen experiments done fairly rapidly after the theory was proposed, and also this whole idea that there could be useful applications of all of this. So for me, that's what really attracts me to this whole field. So what is quantum metrology? Well, it's all about using quantum effects to try and get some enhancement in sensing or metrology. And the question is, when do we get a real advantage? We know that sometimes quantum advantage is subtle. It doesn't just apply to anything. You have to think about very particular scenarios where it does give an advantage. And there are some applications that are already up and running. So in LIGO, I mean, LIGO's crazy, isn't it? I mean, the degree of precision you have to get in that is just insane, really. 10 to the minus 18 meters over 2 kilometer long arms has to be measured. And so any advantage you can get is incredibly valuable. And quantum effects have started to be used in that to give a factor of 2 precision, roughly, slightly less than a factor of 2 precision on those arms, which, because of volume effects, which is length cubed, enables you to measure 8 times the volume of space to detect binary black hole mergers. So it's really useful for things like that, and is currently being deployed. Quantum metrology, I think, is quite interesting. It actually also enables you to do certain things that actually wouldn't be possible without quantum effects. So one good example is detecting biological samples, where if you want to measure something, you have to impinge on it a certain flux, and if it's a delicate sample where that amount of flux would denature the protein or the molecule you're looking at, then you're in a bit of a catch-22. You can image it, but you're going to destroy it. Whereas quantum metrology enables you to perhaps do that with a lower flux. So you can have your cake and eat it, you can measure the sample and not destroy it. So it's quite interesting and useful in that regard. I think it's fascinating when you can start. It's like a quantum advantage. You can start to do things that actually wouldn't be possible otherwise. So I thought I'd give a little bit of a tutorial on quantum metrology before I talk about some of the research that we've been doing at Sussex, because I realize most people here are probably coming from a quantum computing background, and it might be useful. So the simple way of understanding quantum metrology or quantum sensing is in terms of an interferometer that I'm sure you're all familiar with. We have these 2 paths. There's a path length difference or a phase shift on one of those paths, and the probability that we detect photons at the outputs is a function of that phase shift. So if we measure the population of the 2 outputs, then we should be able to infer what that phase shift is. And it turns out that we can do that with a precision that scales as 1 over the square root of the number of particles that we put into the interferometer. Okay, so that's with individual particles that aren't entangled. What happens if we do it with entanglement? And I'm going to take the case of something called a noon state. We heard about it yesterday, I think, from Irfan's talk and perhaps from others. So this is sort of an archetypal state for quantum metrology. It's highly entangled. It has all n particles going one way, and at the same time, all n particles going the other way. And if you do that, you find that you get an enhancement of the phase by a factor of n, and all your probability distributions go up by, you pick up this factor of n here. So your fringes wobble n times faster. And sort of a hand-wavy way to think about why that might be useful is that if you have something you want to measure and you've got a ruler with centimeter marks on it, you know that you can measure things to within some reasonable fraction of that smallest unit, a centimeter. But if you have millimeters or micrometers or something smaller, then you can measure much more accurately. And so these fringes wobbling much faster, in a sense, are like the gradations or the marks on your ruler. And so by having them wobble much faster, you can measure much more precisely. And it turns out this enables you, in principle at least, to measure with a scaling that goes as 1 over n rather than 1 over square root of n. Okay, so you get a nice improvement there for large n. And this has all been done experimentally. You can see various noon states have been created and tested, and you see this increase in the frequency of the states. Okay, so that's the that's the quick, short introduction to why entanglement might help us with these things. Now I want to generalize this a little bit and talk about some of the latest results in this area. So a general metrology scheme always looks like this. It starts off with some probe state that you put in, so some general quantum state. You then allow it to undergo some evolution, and this evolution will encode the parameters that you want. So the things we want to measure are these thetas. So I've got that as a vector there. We can do it as a multi-parameter estimation. We then make some sort of general measurement, and from those measurement results, we come up with an estimator of those parameters. So that's the general scenario. I think it all makes sense, but all of these bits are fairly complex and detailed. We need to optimize over them, and there's interplay between all of them. And really the art of metrology is doing that, optimizing over all of these things, and also trying to do it, I think, in a way that is practical. You can, as a theorist, devise the perfect measurement that you can make there, but if you talk to an experimentalist about it, it might not be realistic at all. So trying to come up with something that comes close to the optimum, but is also physically realizable, is where the art comes in. And a lot of what I've been doing recently has been thinking about pushing quantum sensors into new regimes. So I guess looking at what the interest is in applications and seeing whether we have the right mathematical framework in place to enable that. Because actually there's some lovely theory that allows us to describe quantum metrology, but there are some assumptions within it, which means that often it doesn't apply where we want to push them to. And so I've been looking at how we can extend that theory to make sure that it is applicable in those regions. So some of the things I've been looking at are shown here. They overlap, so I've drawn it as a bit of a Venn diagram. Low data, for example, we might want to have sensors where we operate in some sort of stealth mode. So we send out a low number of photons, we hide them in the black body radiation background, we have a small number of photons that come back. The question is, how well can we sense something with that really low data count? Network sensors, that's going to be the main topic of what I talk about. What happens when we have a whole array of sensors and we connect them? How much better can we do? When do we get an advantage? And connected with the networking of sensors is how do we go about directly measuring functions of parameters? And I'll say more about that in a minute. So let me start with low data. Oh, sorry, yes, I'm also going to fold security into all of this, actually. That's quite an interesting new direction, is how we can make all of this secure. Okay, so let me start with low data. So my interest in low data was piqued when some proposals came out for applications that were looking at how well you could do when you were dealing with a very small number of photons. And in particular, this paper from the Shapiro group at MIT from 7 or 8 years ago, where they were talking about doing LiDAR to measure the position and the speed of a remote object based on the return of a single photon. Okay? So it was the single photon that got me, because this is extreme low data, right? You don't get any lower than that. And it was interesting because there's this beautiful theory for describing quantum metrology in terms of something called the quantum Fisher information. So if you're not familiar with this, don't worry, you don't need to know the details at all, but there's this quantum Fisher information matrix that you can calculate, which is really quite a beautiful thing. It depends only on the quantum state rho. We have these things L's, which are called symmetric logarithmic derivatives, but they're determined entirely in terms of the rhos as well. So actually the quantum Fisher information depends only on a quantum state that I can provide you with. And it's useful because it's connected via something called the Kramer-Rao bound with the precision of all the parameters that you could measure. So in particular, the lower bound is given by the inverse Fisher information divided by mu, which is the number of measurements you make. Okay? So this is great. It's a lovely mathematical tool. It means if I give you any quantum state, you can immediately tell me what the theoretical best precision I can get using that in a metrology scheme is. And it's really nice because it optimizes over everything. So if I go back a few slides to the general scheme, it basically optimizes over all of this. So all you need is the input state and the rest follows. So it's a simple thing, relatively simple thing to calculate, and it's really, really handy. But it has this I wouldn't say hidden, but there's sometimes overlooked assumption within it that it is only strictly valid in the asymptotic limit where you make lots of measurements. So sometimes people are tempted to apply it in the low data limit and you'll get results that are nonsensical or inconsistent. So what do we do? This is the prevailing framework. People are now starting to look at applications where they want to do this with a single photon. We don't really want to give up this framework because it's so nice and so elegant, but we need something new. So we set about developing a new framework for this, so a generalized version of the quantum Kramer-Rao bound that was valid in the low data limit as well as the high data limit. And I don't want to talk through all the details of the mathematics here, but the bound is the top line given there. And what we see is that it has quite an intuitive form, I think. It's got, the first term there is essentially the prior information. So that p theta is your prior information about the parameters that you're measuring. So the first term is the variance, your initial variance before you've made a measurement. And then as we make more and more measurements, we reduce that mean square error. We subtract the second term. And that second term, for people who may have seen a little bit of quantum metrology, looks very much like the Fisher information. It has the same form, except that the S's are defined, again, don't worry about the details, but they're defined a bit differently than how the L's were defined on the previous slide. So it has a structure that makes a lot of sense, but, you know, as always, the devil's in the detail. But the nice thing about this is that we were able to show that it is optimal. We were able to prove that it's optimal both in the low data limit and in the asymptotic high data limit. And we published that in a paper here. Unfortunately, the bottom of the slide is cut off. I don't want to do injustice to some other people, but another group also came up with the same result using a different approach, actually, a geometric approach, which was really nice to see. So that was Peter Cox's group at the University of Sheffield. So what does this look like? If I plot it, so I've plotted the mean square error here vertically against the number of measurements that we make horizontally. And the dashed line is the Kramer-Rao bound. So this is what you would get from the standard framework of quantum metrology. And the solid line is what we get from our new bound. And what you see is that they both agree in the asymptotic limit of a large number of trials, as you would expect and hope for, but that you get this violation of, you know, the Kramer-Rao bound was meant to be a lower bound, and you can see we can do better than that at the low data limit. And you can do better than that at the low data limit. And here we've got about an order of magnitude improvement. Actually, you can do much better than that. It depends on the exact details of the measurement scheme you're making. And so I don't know why that keeps skipping forward. So you know, it's interesting, firstly, that we're able to do this. And secondly, I think it's really useful. Thank you. It's going, isn't it? Thank you. I appreciate that. But also it gives us this opportunity to do a whole lot better in the low data limit. So, you know, an order of magnitude is a huge amount of metrology, and we've got this big window of improving precision down there. So that's quite an exciting area to explore. Okay, so that's a quick summary of low data. Now I want to talk about networking of sensors. So networking is something that we see with sensors all the time. You see large arrays of telescopes in deserts and other places around the world where the data from all of the different telescopes is correlated. And the reason for doing that is that you can effectively have a much larger baseline telescope without having to build a much larger telescope. So it gives you better image resolution and directionality and things like that. LIGO, another great example. We've got LIGO detectors emerging around the world now, and LIGO has to measure to an incredibly precise degree, as I mentioned before, and so noise discrimination is absolutely crucial to something like that. So being able to have detectors around the world so that you can discriminate local noise sources is very, very important. This is another project I'm involved with, which is a network of atomic clocks around the world, which are being used to look for dark matter. So even though these individual sensors are quite quantum, atomic clocks are certainly quantum, LIGO is certainly quantum, I'm calling these classical network sensors because the data between them is being compared or correlated in a classical way. But if we have quantum sensors, there's something more we could do. We could entangle them, or we could have quantum correlations between them. And the question is, does it enable us to do better, and in what situation, and by how much? I'm going to pause for some water. And that wasn't an obvious, the answer to that wasn't obvious. So we set about looking at that. And so imagine we have some sort of network of sensors here. Each of them are measuring a different parameter, some phase, phi 1 through to phi 6. And what we found, what we were able to prove actually, was that you get an advantage by using entanglement if you want to measure some function of those parameters, so some global property of all of them. So to take a simple example, suppose we want to measure a sum of all of those phases. We're not interested in the individual phases, we just want the sum. Then if you use something like a GHZ state, then it's quite clear from this example, you just pick up the sum of the phases and you can measure that directly. And you get a square root n improvement, where n is the number of sensors that you have. So we were able to prove that whenever you have any function, linear or nonlinear, that entanglement will help. And it's an if or only if. So if or only if you're measuring some function of the parameters, then entanglement will help. And the degree of improvement you get depends on the nature of the function, the details of the function you're trying to measure. And I should say that Alexei Gorshkov's group at the University of Maryland did a lot of really great work on this as well. So following on from that, there was a lot of theory and some really nice experiments that followed as well. This is only a very small sample of it. But I think what excited me the most is the fact that a lot of applications are being proposed out of this work now. So there's I've been cut off a bit at the bottom, but there's ideas for phased array directional radar. There's ideas on atomic force microscopy. There's ideas for fiber-based temperature gradiometry. So lots of really interesting measurement schemes where you want to measure differences or functions between parameters at different locations. And entanglement can really help in those situations. So this is the first experiment that was a proof of principle of this idea working. And so the setup is this. There's a generalized interferometry scheme made up of beam splitters. We've got an optical parametric oscillator for squeezing. And the idea of this was to measure the sum of those four phases, phi 1 through to phi 4, by different methods, and to compare them and to see what does best. And so what they did in this paper from 5 years ago now was they started off by just taking the standard approach of measuring each of the phases individually, just with a coherent state, and then summing those four phases. And not surprisingly, what they got was the standard quantum limit. So this is a plot of the measurement uncertainty versus the number of photons in the state. So they got the black curve, or the standard quantum limit. They then tried again using the OPO to squeeze each of the individual states. And of course, by reducing the fluctuations in the phase for each of them, they were able to do better and got the blue curve. So again, they're doing it in a separable way. They're measuring each of the phases individually and then adding them. And then finally, they did it by entangling across all of the phases and measuring that, and they were able to do better again. So this was a really nice first demonstration, a first proof of principle, if you like, showing that if you're trying to measure a function of the parameters, that entanglement can really help. And since then, there's been a lot of follow-on papers that have looked at different aspects of this metrology scheme, dealing with things like noise. This last one, which should appear soon, I think, is really interesting, where they look at how you deal with noise and how you eliminate noise if the noise has a different spatial profile from the signal that you're trying to measure. But all of these, I think, are really nice developments on that idea. So I want to talk about one application. This is an application that came out of the Lucan group at Harvard quite some time ago now, about 10 years ago. And when it came out, it really caught my eye. It seemed really interesting, but it also seemed, to be honest, a little bit far-fetched. It seems a lot less far-fetched now, the way things have developed. But it was an idea for creating a global time standard. Now, the way time standards work at the moment is that countries have their metrology institutes, they have their atomic clocks, their time standards, and there's a journal where different metrology institutes compare their clocks periodically, and they recalibrate them and agree on a global time standard. So it seems like a little bit of a untechnical way of dealing with a very technical issue, having that journal, and it would be quite nice to get rid of that journal, and it would also be quite nice to always push forward for better and better precision with your time standards. And so that's really the basis of this idea from this paper. It was to have a network of satellites orbiting the Earth with a really precise atomic clock on each one, and to entangle those atomic clocks. Now, based on what I talked about, how you can measure a sum or a function of things using entanglement with a better precision, we could apply the same ideas to this, and somebody on Earth could measure directly the sum or the average of these clocks, frequencies, and even do it in a weighted way. So if one of the clocks has a better precision than the others, you can change the weighting of that. And that would directly measure the average. So you'd do away with the journal, and you would also potentially do better in precision because you would get the square root improvement. So you win twice, which would be really good. And there's a little padlock here. You can also potentially do it in a secure way, and I'll talk about that a bit more in a moment. So this seemed a little bit far-fetched because how are you going to entangle clocks on satellites? But great progress has been made with this. So a couple of years ago, this experiment at Oxford showed that you could entangle 2 atomic clocks on the scale of an optical bench, so a couple of meters. Also about the same time, there's some great work going on in Innsbruck showing that you could entangle ions 230 meters apart, and I believe they're now working on extending that to 50 kilometers, so the distances are getting bigger and bigger. And of course there's the fantastic work of Zeilinger and Pan distributing photonic entanglement around the world. And so the prospect now of entangling clocks on satellites doesn't seem so wacky, and I think this could be a really exciting prospect for the future. Okay, let me turn my attention now to security. Take another little break. Okay, so how do we fold security into this? We tend to separate quantum technologies into different pillars. We have quantum communications, we have quantum computing, and so on. But of course, the same physics underlies all of them, and there's no reason why we shouldn't be able to hybridize these things. And there's a lot of work being done on secure quantum computing, for example, and we should be able to do the same thing with metrology. So, we might want to monitor someone's health remotely and have that information sent back to us in a way that no one can intercept that secure information. Or we might want to monitor a secure facility, or we might want to do something in a way that people can't spoof the information and give us a false signal. So we decided to have a look at this and come up with a scheme that's as simple as possible. Our motivation was to do something really, really simple, and our motivation for that is that we wanted it to be experimentally accessible and experimentally accessible as quickly as possible. So this is the scheme. We've got 2 parties, as usual, Alice and Bob, with an eavesdropper, Eve, in between. Alice sends eigenstates of the Pauli X and Y operators through a quantum channel to Bob. Now, the key to the secrecy, the security, I should say, of the scheme is that only Alice knows what states have been sent. So that's the secret bit. Bob can then do one of 2 things. He can either use that state to make a measurement of some phase. This is the phase that Alice wants information about. Or he can do some sort of fidelity check of that state. And all of this information is sent back to Alice through a classical channel. So, yeah, 2 parts to it. It's a little bit similar to BB84, but it's different for reasons we will see in a moment. Not least that there's metrology in there, but also the asymmetry of the scheme gives some advantages as well. So if we focus to begin with on the measurement bit, so the bit where Bob encodes a phase on the state and makes a measurement, then we can draw up a little table of the probabilities of all the different outcomes happening. So on the left here, we've got the different eigenstates that Alice sends, the 4 different secret eigenstates. Along the top, we've got the 2 measurement outcomes that Bob makes. And then you can see a table of very simple probabilities, just in terms of sines and cosines of the different events occurring. Now, what Alice can do, because she has the full information, she knows what state she sent, and Bob communicates back the measurement result. She knows which of these 8 boxes each measurement lies in, and so she can count up the number of results in each of those. And that gives us these numbers N1 through N8 here. And so you can just do some simple Bayesian analysis to come up with a likelihood function of what the phase is. Eve, on the other hand, is not going to know which state has been sent. She will know the measurement outcomes, but because she doesn't know which of these rows we're in, all she can do is average over the different boxes. And you see that if you do that, the result becomes independent of the phase. And so she should, at least in theory, get no information about the phase that's been transmitted. So if we see what that looks like and plot this likelihood function, then, okay, you get different results for the sigma x states and the sigma y states. But if you put the 2 of them together, you get that nice yellow peak there. So that's what Alice sees, okay, from all of this data that is transmitted back from Bob. She gets a nice sharp peak that, of course, gets narrower and narrower and hones in on the true value of the phase. Whereas in theory, Eve should see nothing. So the reason Eve sees nothing, of course, is because she doesn't know which of these eigenstates has been sent. So her strategy would be to try and find out which eigenstate has been sent, and to do that she has to attack the quantum channel, and as we all know, if you attack the quantum channel, you're going to change that state. And the probability she gets away with it is 3/4. 3/4 because half the time she's going to guess the right eigenbasis to measure in, so she'll get away with it, and then the other half of the time, Bob will get a measurement outcome that actually corresponds to the value it should have been anyway. So 3/4 of the time she gets away with it, which sounds pretty good, but of course she's got to make multiple measurements and not be caught on any of them. And so we get this sort of scaling that we see in BB84, where the probability of getting away with not being detected goes as 3/4 to the power of the number of measurements that are being made. And so we're going to see that that becomes exponentially difficult for her to hide. So I've mentioned BB84 a little bit. In BB84, there's a well-known vulnerability called the photon number splitting attack, which is that it's very difficult to make states that have exactly a single photon in them. What's usually done is very highly attenuated coherent states are being sent, where most of the time there's only a single photon there. But every now and then there's more than one. And when there's more than one, the vulnerability is that Eve can skim off a photon and wait until Alice and Bob reveal to each other publicly what basis they measured in, and then measure in that basis and gain some information. The nice thing about this scheme is that there is no such sharing of what basis they measured in. All the secrecy is held by Alice. They never have to share that information. And so if Eve does manage to skim off a photon, she's not able to wait and measure on the same basis. The best she can do is to try and make some measurement on that single photon to find out what state it was. And you can only get partial information on a single measurement on a quantum system, as we know. So comparing the information gain that Eve gets with BB84, you can see it down here. Don't worry about the scales and the numbers, but you can see that BB84 is the purple curve, and this scheme is the blue dash curve. And so you do significantly better on that, which I think is a really nice feature of this and adds to its security. We've also looked at a whole raft of different attacks actually on this. One is something a bit more sophisticated if Eve attacks both the quantum and the classical channels. So imagine that Eve attacks the quantum channel. She knows that it's potentially going to reveal herself. So what she then does is she manipulates the classical channel later to say, you know, if Bob did make a fidelity check on a state that Eve had measured, she doesn't want Alice to check it, so she says, I'm going to flip the data to make it look like Bob actually measured the phase, and then Alice won't check that one. So that's a potential way of covering her tracks. However, you can hide that with statistical approaches. So, for example, you can agree that Bob will make a certain fraction of fidelity checks and a certain fraction of phase measurements. And you're going to find that this distribution gets asymmetric very, very quickly because Eve is only going to want to switch from a fidelity check to a phase measurement, not the other way. The other way would certainly reveal that she'd done something. And so what you're going to do is you're going to skew this distribution, and a statistical analysis would show very quickly that she's trying to play that strategy. And yeah, well, here's some results here. You can see that Alice gets a very sharp peak, whereas Eve gets that relatively flat blue dash curve and gets very little information. I'm not going to say much about this, but spoofing is a big issue. Eve may not be so much interested in getting the information that's being transmitted, but might want to mess things up for Alice, might want to make her believe that she's getting true information, but actually change that. And there are well-publicized cases of where people have done this with GPS systems and other global navigation systems to try and make people think that they're in the wrong location. And so it's a big issue for both military and civilian applications. I'm going to skip over this, but there are ways that you can make this scheme secure to those sort of attacks as well. So what I want to get to now is an experiment that was done on this very recently, came out in the archive just a few weeks ago, where it's precisely the scheme I've been talking about. It was done with photons through a 50-kilometer optical fiber using telecoms wavelength photons. And the 4 states were encoded in 4 different polarizations of the photons. And it's exactly the scheme that I was describing. And here are the results. So what is shown here is they were able to calculate the Fisher information for the 4 different states that Alice was sending. Now remember I talked about Fisher information before. It's a measure of how well you can use a state for metrology. And for these particular states, the maximum value is 1. And what we see here is that for the 4 states that Alice sends, Alice is able to get a Fisher information very, very close to 1. So it works almost ideally. Eve, by contrast, should get no information. This is her bar here. She doesn't get none, but this is a logarithmic scale, and so if you look at it, she gets less than 1% of what Alice gets. So, this is a really nice demonstration of the information asymmetry in this scenario. So that's the information asymmetry. What about the actual results? Well, this is a plot of the true value versus the estimated value vertically. The triangles are the measurement data, and the red dashed line is what we would expect. And so you can see that we're able to predict the phases quite accurately there. And there was some nice analysis also of the errors and how close we get to the Kramer-Rao bound. Okay, I think I have a few minutes. Do I have a few minutes? Where's our chair? Okay, I'll carry on. I've only got a couple more slides, I think. So let me talk about networks now and how we put all of this together. So essentially, how do we fill in this middle sector of the Venn diagram where we're looking potentially at load data, we're looking at networks, functions and parameters, and we're folding security into all of this. How do we generalize the scheme I've just talked about? So we're going to do essentially what we did before, but we're going to have one Alice now and lots of Bobs. And I'm going to make the assumption that there's no communication between the Bobs, and this is for good reason. If there's classical communication between the Bobs, that would be a real security risk. If there is quantum communication between them, then the Bobs are going to need to have a way of doing quantum key distribution, which might not be practical or viable. For example, if you want to put these on satellites, you want to reduce your payload. But more fundamentally, it kind of undermines the whole spirit of the scheme, where what we want to do is have a hybrid scheme where we seamlessly incorporate sensing and communications. We don't want the bobs to measure their phases and then have to encode it on a key and then send it that way. So what we're going to do is we're going to get Alice to send an entangled state now to all the bobs. So imagine something like a GHZ state, 1 qubit to each of the bobs, and there's this phase chi here, which can take one of 4 values, and that value is secret to Alice. So this is the secrecy that we saw before in the 2-party scheme. And then imagine the bobs encode some phases, so they take the lower path of each of their measurement devices. Then what we're going to get is we're going to get a sum of all their phases encoded on the state. Now, based on Bob's measurements, Alice should be able to infer what the sum is because she will know what the chi is. Okay? That's secret. No one else will be able to uncover the sum of the phases because they won't know what the chi is. So that all should work fine. The problem with this scheme is actually in making it secure. And the reason for that is that in order for Alice to check whether there is an Eve attacking those states, she needs to compare Bob's measurements with the state that she sent. The state she sent is this one, so she needs to compare this with that. And the only way it will be the same is if the sum of the phases is 0. And the only way the sum of the phases will be 0 is, well, actually there's 2 ways. By coincidence, the phases could add up to 0. But more likely it's going to be if all of the bobs take the upper path and just do a fidelity check. Okay? And because they're not communicating with each other, they've got to do that randomly. And so it's going to become exponentially unlikely that that happens as we have more and more bobs, right? So this whole scheme becomes exponentially inefficient in detecting an eavesdropper. So a way we can get around that is with a hybrid scheme where we sometimes send separable states. So these are just the states that we had in the 2-party scheme. And the advantage of that is that now you can detect Eve on any of these paths. It doesn't rely on all the bobs simultaneously making a fidelity check. You can detect Eve on any one path if Bob checks that fidelity. And sometimes we're going to send an entangled state, just as we saw on the previous slide, because this will give us the quantum enhanced precision. So by using some sort of hybrid between the two, hopefully we can get the security and some quantum enhanced precision as well. So we're going to send these states with different probabilities. The first one we'll call PS, the second one 1 minus PS. And then what we can do is we can do some simulations and see what sort of results we can get. So these simulations were found by minimizing the measurement uncertainty. That's what this quantity is here. So this is Alice's measurement uncertainty. And we're plotting it as a function of the number of detectors. So I'm going from 1 to 6 detectors. And I'm optimizing over the probability of sending separable versus entangled states, and I'm optimizing also over the probability we do a fidelity check versus a phase measurement, and I'm constraining it by the fact that Eve's information is no better than that red line at the top, okay? So that's a very broad distribution, a standard deviation of 1, so we're constraining the maximum amount of information Eve can get. Okay, and if we plot this, then we see some interesting results. We see for small numbers of bobs, we get a much better measurement precision than Eve. So we're getting this information asymmetry. But as we go to higher and higher bobs, we see that if we only use entangled states, the precision gets worse and worse. In fact, if I go further, it goes very rapidly up. And the reason for that is that, remember, it becomes exponentially inefficient to detect an eavesdropper. And so if I need to maintain that red line for Eve, I have to put more and more of my resources into security and less of my resources into making the measurement. And so the measurement gets worse and worse. If I use only separable states, I've got the purple dashed line, and that's pretty good. It maintains security, and it gives me quite good measurement precision, but it's not quantum enhanced. And then finally, if I do the hybrid scheme, I get the blue dashed line at the bottom, which does better than either. And actually, we've pushed this out to a large number of bobs, and you see it's quite flat. So that's really interesting, we think, because it means that this is almost independent of the network size we're looking at. Okay, I'm going to wrap things up there, but I think just by way of summary, what we're looking at is trying to, I guess, motivated by applications that are coming out, trying to push the theoretical underpinnings of the treatment of quantum sensors and quantum networks into those regimes so that we can properly describe them and come up with new protocols that are close to experiments at the moment so that they can be tested rapidly and hopefully developed into exciting new applications in the near future. So I'd just like to thank the students and postdocs that did all the work. I just came along for the ride, and the various bodies that funded me as well. So thank you very much. I guess it's time for questions. Is it time? Yeah. That's yeah. That's a really good question because that's one of the assumptions that go into the derivation of the Kramer-Rao bound is that you have, well, it's a generalization of Gaussian functions actually, and that's one of the things that breaks down. Also, I should use this, also the prior information is not accounted for in the in the Kramer-Rao bound, and the reason for that is, in the asymptotic limit, prior information won't matter because you're going to be completely swamped by your measurements. Right. So you've got to put that back in. So there are a few things. I mean, the way we went about doing it is just went back and went through the original derivation of it, but didn't put the assumptions in, essentially, which was quite a fun exercise.
So if I want to take advantage of that low measurement limit, can I post-select? For example, if I'm trying to pull out a singular signal on a background?
Yep, you can do that. Yep.
Okay, and maybe one final piece.
Yeah,
you had this beautiful expression, which I didn't completely catch quickly, the commutator of SI and SJ. Is there a way to sort of back of the envelope understand the intuition for that constraint?
I'm not sure there's a back of an envelope one, but yeah, I mean it's quite, so that's when the bound is separable, right?
Yes.
So yeah, so let's talk about it afterwards. I don't think there's an easy way. Okay. You can, there's a nice mathematical proof of it, but yeah.
Yes. Hi. Thank you for the very informative presentation. Over the years, I've seen a lot of topologies where you have a single Alice and multiple pops. The thing is, from an experimental point of view, pops are usually very expensive, resource expensive to make. Are there any topologies that have single pops and multiple Alices? Single pops and kind of pop-centric topologies?
So multiple Alices measuring a single phase. Yeah, I mean, certainly you can do that as well. That's a different scenario from the one we were considering, of course. I mean, the reason we looked at this particular topology is that we wanted to exploit the advantage you can get by the quantum enhancement of measuring functions of different phases. But what you're talking about is measuring a single measurement that multiple parties share. You can certainly do that as well. You won't get the same quantum enhancement that I've been talking about, but it's a really interesting scenario. Yeah. Any more? If not, I'll rest my voice. Thank you very much, everyone. I got there.
Thank you, Professor Jacob, for the insightful talk. I know much more about quantum sensing and metrology than before. Our next speaker is Engineer Mohammed Al-Sayari, the chair of the Saudi Quantum Computing Association, to give a glimpse about the association.
Thanks, Dr. Mohammed. Assalamu alaikum jami'an, and good morning, everyone. Can put it in display, thank you. Today, yes, I would like to give you some overview of the newly established Association of Saudi quantum computing. It will be, I promise you, it will be a very quick presentation. I would like to start first of defining what's the technical associations and what's the roles of those ones. So when you talk about a technical association, it's really an organized group dedicated to advancing certain field under the technology. And it plays a vital role in empowering the ecosystem and advancing that one through lots of things. It cares about innovation, bridging the sectors and building some synergy between academia, industry, and governmental entities. And it helps in shaping the policies and strategic directions for that technology itself. The same goes with, of course, the talent and developing skilled workforce. This is very critical role of the technical associations. Public awareness and driving also international collaboration in that field is very important. Types of technical associations, you have multiple ones, one of which is the industrial association. Here, companies would work together to have some commercialized and application. The same, and these are some examples of those associations. Academic and research institutions is also, association is another example where researchers and academic institutions will work together to produce some scientific papers and scientific advancement in certain fields. Similar goes with professional societies and non-profit organizations and the also international councils and alliances for policymakers. Bear in mind that it's not isolated or silos. You would find lots of interference between these entities. For example, you would find some non-profit organizations that would work on scientific, academic objectives, and the same goes with other fields. So back to our newly established association, the Saudi Quantum Computing Association. This has been established in Q3 of 2024, and specialized in quantum computing and technology. It's a non-profit organization, which means that it's licensed by the National Center for Non-Profit Sector and supervised. Our technical, in fact, sponsor is the Ministry of Communications and Information Technology. In fact, the association was created with I would say the top technical people in the field, people who are working on or leading the quantum in Saudi Arabia. For example, when it comes to the academia, you would find Dr. Mohammed Filimban. He's a co-founder from KFUPM. Dr. Sumaya Madkhali from Jazan University. The same goes with, I would say, academic institutions, KAXT, Dr. Saad Al-Wayed. The same goes with, from industry, myself from Aramco, and here from the government, you would find Wazat al-Ittisalat. And the same goes, we have an extended also people or organizations that closely work with us on building this one. Our vision is to be the leading entity in supporting and advancing the quantum computing development within Saudi Arabia. In order to reach that, we need to empower and support the ecosystem in Saudi Arabia by, of course, raising awareness, fostering scientific research, and promoting innovation, and collaborating between and building this collaboration between academia, industry, and other entities. And our values goes under innovation, collaboration, excellence, and leadership. In order to reach those, I would say, vision and missions, we have certain objectives that we are working to meet. For example, knowledge spreading or knowledge dissemination and expertise exchange. This is a very, very important point. Here, this is for professional people. We need to work together with them to have this platform. When it comes to public awareness, for general user, I would say. Also, we need to have this outreach campaigns and educational initiatives to introduce the quantum to the broader community. Human capital development, developing people is very important for us. We need to work with universities and training education institutions to help to bridge the gap of for the skills gap within the quantum computing. The same goes here with consulting and advisory services. In fact, we plan to be the, I would say, the trust, independent, unbiased entity that organizations would reach us to get some clear, I would say, direction, strategies, or roadmaps for the quantum, because we have, I would say, the top people within the association that they will bring unbiased decision to those organizations. The same goes with developing like these certain help in doing the applications or software or algorithms, establishing in fact, this is a big one that we would like to establish this community that would collect all the entities together. And another one is really enriching the Arabic content. And I always bring this example, the word quantum computing, and this is a question to all. Quantum computing, what does it mean in Arabic? الحوسبة الكمية or الحوسبة الكمومية. Who's saying الحوسبة الكمية, please raise your hand. Okay, الحوسبة الكمومية. Okay, who's correct in that case? So this is just one example that we really need to have very clear standards, very clear like terminology for the quantum. So researchers or any book or universities or schools that would have some Arabic content, they can get advantage of that type of product in order for us to be on the same page. And I always give the example of for example, the mobile, this one. And in Saudi Arabia, because we had the translation al-jawal, so we say al-jawal. And other Arabic countries, they call it mobile. The reason is that they did not act quick to have it public to people. Yeah, our target audience, as you can see, we target people from students to university people, researchers and academics, even for industry professionals and technical people. And of course, general purpose or general public is another one. These are small set of activities that we started and we plan also to continue doing the flagship seminars and conferences, having networking sessions, having awareness, of course, campaigns. And this one we have started so far, I think we have done 3 or 4. And the strategic partnerships and collaborations, I believe we started drafting some agreement with either like governmental entities or academic institutions and some quantum companies to help us to achieve our goals. Hackathons and competitions are the next one. So, as I promised, it's very quick. These are the website if you would like to get more information, and this is the email, and the social media are here. I encourage everyone really, be it like a researcher, a student, or someone interested in the quantum, to join this association. We have a booth here. I delightfully invite everyone to go there to get more information. Thank you, everyone. Thank you. We started, the process takes some time in order for us to officially announce the membership. But so far we have, like, I would say, we just started, I think, 1 month back or so. I think we reached 50, plus the 10 people from the community. These are the subscribed members, yes. but lots of follow. I would say in our social media. I did not count the numbers, but hundreds so far. Yeah. Thank you. Inshallah, hopefully, with these programs, with these events, I'm sure we will have. Thank you very much. Thank you.
Thank you, Aziz. So now it's due for a coffee networking coffee break. So inshallah we'll resume at 10:15. So we'll give you about 15 minutes coffee break, inshallah. So see you around 10:15.
الو تست مايك هذا فوق ولا
3, 2, 1 test mic.
Okay, assalamu alaikum. So welcome back. So today, inshallah, or next session will be kind of panel discussion with Dr. Muhammad al-Sharif, the General Manager, National RDIA Observatory from the Research Development Innovation Authority. So please join me to welcome Dr. Muhammad. حياك الله دكتور. تفضل. أول شيء حياك الله دكتور. Very happy to be here with us. Probably this is going to be more like a Q&A or panel discussion, having RDIA as a strategic partner for this symposium. And I know quantum computing nowadays is an important topic, not only for KFUPM, but also at a national level. And in the most recent call for proposals by RDIA, we saw that development of programmable fault-tolerant quantum computers by 2040 is listed as one of the national missions under the Economy of the Future initiative. And I was personally super excited for that, not only because this is my personal interest in terms of research, but I do believe that this is probably the next or the next shift in computing paradigm. So let me ask you this question. What factors contributed to this field, quantum computing and technology, to be designated as a priority focus area in RDIA?
Thank you very much. First of all, Allah يحييك, and thank you for inviting me here at this symposium, and to give me the chance to share RDIA visions actually for advancing Saudi Arabia's quantum technology ecosystems. At RDIA first, so before answering your questions, at RDIA we are driving the Kingdom's mission to become a global leader in quantum innovation under the Economies of Future national priority. Indeed, quantum computing is more than a technology. It's a national priority to secure technological advancement and independence, and also to drive the economic diversification for the kingdom, in addition to tackle any complex societal challenges. Going back to your questions, Dr. Muhammad, for how did we actually identify the national mission, which is about fault-tolerant quantum computers by 2040. First of all, we adopt 4 main factors to identify the national missions generally. By the way, we come up with a list of 30 national missions, and we have prioritized 5 of them to be launched immediately till 2027. After that, the remaining of those missions will be sequentially actually executed. But going back to the main factors that allowing us to identify the quantum computing or technology in general national mission as a priority, first of all, it does have strategic alignment with the Vision 2030 key pillars. For example, the quantum computer. Actually, it aligns very well with the key principles of having digital transformation, artificial intelligence, and also for cybersecurity, which is part of the Vision 2030 pillars. The second, so I'm not sure of the. The second factor is about global impact potential. We believe that the quantum computers actually would play and can revolutionize actually the industries, and would enable other technologies actually to become to make scientific breakthroughs, not only within quantum space and quantum technology itself, but it would spans different applications and fields, like from drug discovery to energy optimization. The third factor of identifying the national mission in quantum computing, since it's characterized by being bold and long investment project or journey, for that reason designated a moonshot program or mission in quantum technology. Actually, by RDIA, it embodies our principles of pursuing a bold, measurable, and high impact objectives. The last but not least factor that we consider in identifying and prioritizing the national mission, it's actually impact in reducing potential risks, especially in quantum computing, since it's crucial actually to counter any future cybersecurity threats and also to reduce any dependence on imported technologies. Thank you.
Okay, excellent. So you talked about the moonshot program, which obviously needs a long-term investment. So in terms of both infrastructure as well as the funding, I mean research projects funding, so can you give us a glimpse of what kind of programs, funding programs, that probably RDIA can provide for researchers in national institutes?
Yes, perfect. Thank you, Dr. Mohammed. Let me answer these questions into two main parts, since I think the funding schemes and funding models is part of the enabling the national mission and part of building the proper infrastructure. But before funding, let's touch upon the infrastructure that's essential actually to embark such national mission. First of all, we should have a research hubs and like building a specialized zones and research centers in adjacent to the proper and R&D centers. For example, having Dhahran hub for energy, KAUST for building quantum hardware, and also CAX for communication and sensing technologies. This would help to actually make alliance and bring all the scientists and the specialists in that field. The second element in building that infrastructure is to have quantum hardware facilities by developing local quantum hardware that can be used for R&D purposes. This is part of the infrastructure. The third one, without neglecting building the human capital and upskilling the talent in that field, I think it's essential as well, and the key or crucial to have the proper talents who will do and conduct such research. Regarding the funding schemes or models, I think this is connected to the value chain of the R&D and innovation, since started with the discovery, development, and deploy. So we should cover, since it's like a pipeline, and we need to fuel all these stages, building on the multi-year R&D grants, which is already, I think it's, which is already RDIA has launched last year, and there's another cycle this year that, by the way, is targeting the 4 national priorities, and of course, quantum is one of them that falls under the economies of future national priority. This will ensure a long-term funding stability, along with the flagship programs such as Saudi Basic Science Initiative. The second scheme or funding model is to activate or enable the partnership between public and private, so encourage industry and to invest in that field by strengthening the relationship between the academia and the industry, and also RDIA to be part of that funding through what's called SBIR, for example. And I think already, I'm sure, in last week or the week before at LEAP, there's an announcement called Saudi Grants or Saudi Innovation Grants Program that targeting the SMEs or startups who they have like scientific ideas that can be commercialized later. The third schemes could be incentives for commercialization, and this is actually linked to the later stage of the innovation value chain, to deploy and scale up any prototypes or startups actually outcomes to go to the market.
Excellent. So I think you mentioned about three initiatives, to foster this quantum ecosystem nationally. So you mentioned at least three entities, KFUPM, KAUS, KAX, and many others. And I think this is important. This is not a single institution effort. It has to be a collective effort of multiple institutions. But how about international collaboration? Like, how do you see the importance of the or significance of collaboration with international collaborators in quantum, both in quantum workforce development, as well as to establish and facilitate knowledge exchange, but mainly localization of quantum computing and technology?
Interesting questions, Dr. Mohammed. Yes, I think building a strong relationship with the overseas, let's say, organizations or even R&D institutes, I think it's really imperative and key for success launching of the quantum national missions and its related efforts and projects. So one of the main, let's say, program to fulfill this actually direction is to have what's called global talent programs by facilitating, let's say, international fellowships and quantum research residences with the quantum technology or quantum computing actually partners or leaders such as IBM or Pascal. The second program or a second potential program, I mean, could be like joint R&D projects to establish research collaboration between local entities and R&D centers, either from the academia or private sectors, with the global quantum leaders to tackle common challenges or global pressing issues. Also, the talent or attracting international top talent to the kingdom is a key metric of success as well. So by attracting them to join forces of conducting and developing, let's say, R&D and innovation projects in quantum computing, I think this would ensure a seamless knowledge transfer and will expedite the transfer of technology to local talents. Also, actually participating in the forums, the global forums, I think it's important. So this will allow us to showcase the kingdom's advancement and progress in quantum technology in its broad meaning. Also, it would allow to promote knowledge sharing and exchange between the local and global side. Thank you.
Excellent. So I think this was very enriching. I think we talked about the moonshot program, long investment being kindly supported by many agencies, but authorities, but particularly by RDIA. We talked about the initiatives on quantum computing. There are different programs in terms of research funding, but more importantly, we talked about the collaboration between academia, industry, as well as the government entities. We talked about the international collaboration, which is very important to foster this kind of quantum economy nationally, but also, more importantly, to support quantum research. And I think such an event is very important place to have this kind of networking, not only between academicians or researchers, but also between industry as well as people coming from the government. So before I conclude this session, I mean, if you have any concluding remark, anything to say about the future of quantum technology in Saudi Arabia?
Yes, thank you very much. I just have one point. I would like to mention that RDI is dedicated to build a robust ecosystem for quantum technology through strategic investment, international collaboration, and its commitment actually to talent development. By uniting government, private sector, or the industry and academia, will be able to actually propel Saudi Arabia to the forefront of quantum technology. Thank you very much. And I hope I answered your questions, Dr.
No,
Mohammed.
that was very insightful. So please join me to thank Dr. Mohammed Al-Sharif from RDIA. So our next session, our next talk will be by Dr. Hussein Al-Salim, a geophysicist from Saudi Aramco, to give us an interesting talk about an application, a real application of quantum computing in the realm of geophysical.
Thank you so much for inviting me. Thank you so much for the invite, Dr. Mohammed. I really appreciate it, and I'm really glad to be here at KFUPM. So, no worries. So before I start my presentation today, I would like to talk about myself a little bit, just to give you an idea where I'm coming from, what is my background, and so on. So my name is Hussein Al-Salim, and I'm currently heading the quantum and high performance team at ARC, our advanced research center. And I currently heading like about 5 geophysicists. So mainly my team consists of geophysicists. These are in Dhahran. And I have 3 quantum computing experts in our Delft Research Center, and about 3 developers in our BRC Center, which is Beijing Research Center. And we are always collaborating together to work on solving different applications in geophysics. So mainly the problems that we're trying to solve are the geophysical applications. So before that, what made me be part of this team, and what is my history to be working in this type of team? So when I graduated at 2010 from the University of Leeds, I earned my geophysical degree. So my background is geophysics. And then I worked at Saudi Aramco for about 3 years. Most of my work was in the field during my first 3 years at Aramco. They always like to let you see the hard work and so on, especially when you're a recent graduate. So mainly I worked at acquiring seismic data. I also worked as a well site geologist. This is where we drill a well and we describe every feet in the well, actually, to say what types of rocks are there. And after that, I earned a scholarship with Aramco, and I was sent to UC Berkeley. And there I found actually the thing that I liked the most. I was assigned to work at LBL, Lawrence Berkeley Lab, as part of my master's and PhD. And I worked at the NERSC supercomputer that they have there. And so mainly I was solving the wave equation on big supercomputers. And soon after that, I came back, I graduated. And I came back to Aramco, and luckily, this doesn't happen all the time, but luckily for me, I worked on the same thing, solving the wave equation, but not on CPU big systems. We were acquiring the MAM7, one of our biggest supercomputers, and I continued the same work, but this time on GPUs, and it was really fun. But we wouldn't be able to do that if we weren't keeping the tabs on GPUs. Everything we had was CPUs, but suddenly we had something on GPUs, but we always had machines on GPUs, so we tested many things on GPUs before we started. And that's why, after that, and after we ported most of our applications to GPUs, we are tasked about 2 years ago to keep our tabs closed on quantum computers, because maybe at some time there will be a change where we will be using the quantum computers after the GPUs as we transitioned from CPUs to GPUs. Yeah, and that's why I'm going to show some applications, very early applications in geophysics that describe how we can use quantum computers for those geophysical applications. So my agenda will consist of 3 parts. I will give a quantum computing introduction. So here I will relate this to what I know about bits, because this is what I'm familiar with. I'm working with supercomputers, CPU or GPU. So I'm very familiar with bits. So when I want to understand qubits, I always try to relate that to the bits that I know. Next, I will show some problems that quantum computers can solve. What are the problems what is the formulation that we should have before we solve on quantum computers? And then I'll show 2 applications that were relatively successful in applying quantum computers at Saudi Aramco. These include the refraction, residual statics estimation, and the quantum annealing for sparse spike deconvolution. I'll explain those problems and also why they're very important for geophysicists. Okay, so first I will compare a classical bit and a qubit. As you know, the qubit is a sphere, a classical bit is a switch. And when I look at both, from what I know, a classical computer or a classical bit can store data, but and also a bit can be only in one state, either a 0 or a 1. It's just a switch. And n bits, if I have multiple bits, they can solve about n calculations at maximum at one time. And I know bits are disconnected. When I change one bit, it will not affect the other bits surrounding it. And I think Irfan made a great comparison for this too. And the results are precise usually, but this came, at the beginning they were not precise, of course. With time and with the history, they became precise after many experiments and many iterations of the classical supercomputers. And we have a controlled arithmetic error. We always know, like if we have floating points, we know our error is about like the epsilon is 10 to the minus 6, and if we are doing the double, it's about 10 to the minus 16 as an example. We know this is controlled. And funnily enough, the quantum computer is the opposite. It cannot store data. Bits can be in two states at the same time because it's a sphere. And n bits can perform up to 2 to the n maximum calculations. And as you know, bits are entangled. When you change one of them, it might affect the ones surrounding it. And results are usually estimates. We measure multiple times until we get the estimated result. And currently, of course, as many of you know, and many of the presentations prior to this showed, the quantum noise causes error. So I will go a little bit to my journey, where I started with CPUs, GPUs, and QPUs. And I want to show how they relate to each other. So I know with CPUs, usually our tasks are medium in size. And usually I get a result that is also medium in size, similar to the input problem that I inputted to the CPUs. GPUs are great. They are not as smart as CPUs, but they can do many, many tasks at the same time. Quick tasks, but the same tasks. So they were very helpful to our stuff, and they actually, I believe they contributed the most in terms of hardware to our geophysical problems. And from our experiments, or just like short experiments with quantum computers, we understand that they can have a very small task that is very, very hard and can output a very small output at the same time. But they can solve something that cannot be solved by the CPUs and GPUs. So here I'll just explain what is quantum computers and how we understand it through the classical algorithms. So we know if we have a classical algorithm that is simple enough, like calculations, it might take 1 second on the classical algorithms and 1 minute. But as we go with bigger problems like decryption as an example, which takes the age of the universe as an example, it might take 30 minutes on quantum computers with time. So incremental advancements are going on with classical computers as well as with quantum computers. And let's see. So here is the history of the investments for quantum computers. So they started in 1980, the physics of information. This is when research started. And the first quantum algorithm was in 1990. And then the first experimental qubits were about in the year 2000. And then we got better qubits in about 2010. And then 2020, we started getting some quantum supercomputers that have about 10 to 100 qubits. And this is relative to the government funding. So we started with about 1 million in total government spending on quantum computers to about 10 billion. And we're expecting that the value of quantum computers to be projected to 1 trillion maybe by 2040. So the biggest problem we have in geophysics and quantum is finding a problem that we can solve, the geophysical problem that can be solved with quantum computers. This led us to form this graph. Because after many experiments, we failed a lot, actually. Maybe for every 20 things we try, we get one thing that works. So we created this graph based on our experiments. So here I have the year and I have the problem size, and here the feasibility. As you know, with time, qubits increase. So they come with better and better quantum computers, and therefore we can solve bigger and bigger problems as the number of qubits increases. So the green triangle is what we can solve or what we can resolve. So if we see like the problem size, like decryption is an example of a problem size that is big, that is huge. And factorials is a problem that is small. So basically we should be able, since it is a small problem, we should be able to resolve it, as an example, with quantum computers. But there is something that is paradoxical to this. The issue is, as the problem size is bigger, there is an algorithmic advantage with quantum. There is an algorithm that exists that can solve, for example, decryption. But it is difficult to find an algorithm to solve factorials. That's why the only things that we can solve are in where these two triangles collide. So in this zone to the right. So this is where we get quantum computers that are faster and they can solve problems. So we cannot really go and solve big decryption problems, although the algorithms is there. And we need to find problems that are in that triangle for geophysics. And for us, our team in Delft had studied this, and they wanted to decide on what quantum computer to use to start the geophysical journey. So they looked into two choices: the quantum annealers and, as you know, the universal quantum computers. And they decided upon to use the quantum annealers because they can go with because they're optimized to. There is already 100 problems that can be solved on these quantum annealers, and it's easy to form some problems that can fit these quantum annealers in geophysics that are not easily done on the quantum computers that are available currently, because they have more bits here, or qubits than but they can solve only specific problems, more qubits than the universal quantum computers. So our strategy, I'll just show, our strategy at Aramco is to develop currently use cases for the quantum annealers and to monitor the progress through academic collaborations and discussions for the universal quantum computers. And this is what we are currently doing. So most of the applications, the applications I will show today were all done on quantum annealers. And this is a comparison between the current universal quantum computers to the left and the quantum annealers. They can, as I said, they can do only task-specific using the QUBO format, the quadratic universal binary optimization. They have up to 5,000 qubits. We believe their technical readiness is about 8 to 9, while currently the readiness for the quantum computers is about 4 to 5. And there is a few use cases for the quantum circuits, and there is many use cases for the quantum annealers. And that's why we're going to start with this. So these are the problems that we currently were successful in solving using the quantum annealers. They are the residual statics and the L0 norm, which I will get into now. Okay, so this is the quadratic unconstrained binary optimization problem. It can also be called the Hamiltonian or energy function. As you can see, I have two terms. The first term, we call it the coupling term. So this represents the connection between two vectors, if I can say it. And the other term is the bias term. This term is difficult to solve for in regular classical computers. And that's why we're using quantum computers so we can have this penalty term on the right, which is called the bias term. And I'll show you two applications where this is very useful to add and very helpful for our geophysical problem. So we always look at our geophysical problem and always try to formulate it in a way to fit this Hamiltonian or energy function. Okay, and so the first one, of course, this came after maybe more than, I'd say, at least a dozen failed problems that we failed to map onto this Hamiltonian energy problem. The first one is the refraction residual statics problem. So I'll talk about this a little bit. So before that, I'm sure not many of you are maybe familiar with geophysics, so I'll explain this a little bit fast. So before we start investigating area and exploring whether there is minerals or oil or what have you, we start by acquiring seismic data. This takes about 2 to 6 months of time. After that, we do data processing, and it takes about 2 to 4 times. This is cleaning the data, removing the noise, removing the waves that we don't need, and so on. And after that, we have something called imaging, where we turn our data from time domain to depth domain. So we know exactly where to drill. And after that, we send it to the interpreters. The interpreters have many information from surrounding wells, and they can interpret this and convert it to subsurface image that can look like the one to the left there, where the geological features are there, the faults, and everything you need. This, so we acquire every year, we acquire about 10 to 100 petabytes. So that's lots and lots and lots of data, and we're doing this every day. I think there is now 8 to 10 crews acquiring data as we speak. So that's a big amount of data. Okay, but there is one big problem here. This is what I'm showing you here is our #1 problem in geophysics. And I'm talking about locally, especially in the kingdom, the East region. It's called karsting or caves. So this is how it looks like. So when we acquire seismic data, they go through the earth, and they most likely they will hit a cave or something, and then the waves will not travel through, and they will get delayed because the air is slow. It's not like the other materials that we have that are faster. And so when we acquire seismic data, this causes us big issues because it's not like the earth is one layer of caves. It's just they're spread all over the place. This is not just an issue for geophysicists, by the way. This is an issue here for many wannabe homeowners, because many homeowners here want to build and get a house, and they found out after the geotechnical survey that their land is on top of caves. And then they're not allowed to build, and this causes many issues here in the country, actually. So this is not just our #1 issue, but it's also another issue for more wannabe, I would say, homeowners in the kingdom. So one of the things is, so this causes something called residual statics in geophysics, and we want to resolve for that. I'll show you what happens when a wave goes through a karst. What happens to the wave? So let's see. First, this is our main job. We simulate seismic data on supercomputers. This is an example from our software. We do this many times. We send the waves. We consider the earth as acoustic or elastic. We put the velocities and so on. And then we simulate the waves. And this simulates all the reflections, refractions, and all types of waves. And you cannot do this without having big, huge supercomputers, especially GPU supercomputers. So let's see what happens if the wave goes through a karst. So let's say I have my vibrosize. It's doing the same as my simulator did. And it's now sending a wave to the earth. So I'm waiting for the reflections that are coming from the earth. The first 2 reflections are okay. But then I sometimes notice that the 3rd reflection is coming in a delayed time. It's not coming in the time that I'm expecting it to. But it's very difficult to understand where the reflector should be. So this can be like a straight line in the earth, but then the delay does not show that it is a straight line. How do I know that this is coming from the reflector or not? So we have to resolve for this. And so here I'll show like an image. This is a seismic gather where I have this delay in the reflector. And let's say then I process it and I go to the last stage after processing. And let's see, there's something happened. Yes, let's see. Okay, and so after all the processing and all the imaging, this is the image I get. As an example here, and here I see like there should be a reflector, but it's not connecting. Is there something going on here? Or is it the karst at the top that affected this and made this disappear? Is it a straight line or not? Is it a layer or not? So this is where we need to resolve for. And so if I resolve and I get the correct residual statics, if I go back and forth, This resolves the issue of the reflector, and now it becomes the real thing. And many times we don't correct for this correctly, and we might go and drill for this. Let's assume that here there is some oil and gas in this area. So I'll just show like how this looks like. So these waves that are coming, because they're big, their wavelength is huge, they're actually bigger than the whole reservoir in terms of vertical size. So this is how this looks like in terms of an oil reservoir, as an example. It's huge. So getting this right is very important. Getting the residual statics, solving for them at the top is a very crucial issue for this reason. And so this is the seismic image with uncorrected, and this is the seismic image after we correct. As you see, this is my acquired data. It's fixed. If it's not fixed, we get the issue below. Once we fix it, it fixes the final image that we get. Okay, so let's now formulate this problem and try to resolve it using quantum computers. Okay, so let's assume I have two. I have two traces that are coming from the field. Okay, one is, let's say this is the first one to the left and the first one to the right. We usually do a normal move out with a specific velocity and try to make them straight so that when we stack them together, they become a straight line. Okay, so there are many possibilities of adding delays to these two in order for them to stack on top of each other. So we can let them be and add them, and we'll get the result to the right. We can add a delay to one of them, okay, and then add them together and get the maximum energy. And this can be formulated as a maximization problem where each one is my data, and we add them together to see what is the maximum. So we can calculate the L2 norm to get the maximum power, and the input is the delay. TI here is the delay. We have to find the best delay that makes these stack on top of each other and get the results that we are striving for. Okay, see, so these are all the possibilities, just for two. I haven't added all my data, just two traces. And these are, let's say I only included the delays from plus 40 to minus 40, or minus 40 to two traces. And I plot all the possible values or results for this equation to the left, and you'll see like where the global maxima is. And this is just for two traces. And imagine that the values that are possible for more than two traces. And so here, now I know my Hamiltonian, how it looks like. We have the coupling terms and I have the bias terms. So to represent this in the Hamiltonian, I have my weights. I call them Wij. Ij stands for the traces. T and T theta stands for the delay for trace 1 and delay for trace 2. And I have them all together. So this is the dot product between them, given a trace and a second trace and a shift for first trace and a shift for second trace. And then what I can add here, what is great about quantum computers, I can add a bias term. So the bias term here is the second term, CT. And this can be, as an example, the delay, the absolute value of the delay. So if I have the absolute value of delay, I can control whether I want many delays or not many. So if I add the penalty term, it will affect the number of delays I'm adding. So if I don't want to have so many delays, and I'm not expecting many delays, I can control that through the bias term at the end of the bias term in the second term of the equation. So I have my quadratic part to the left, and I have my bias term to the right. And I can input this equation to our quantum annealer to solve for the delay. And this is an example of solving it. So this is what we input usually to the quantum computer. This is the other issue with quantum computer. We cannot input a big problem size. Like this is like a regular, I'd say medium-sized thing that we can enter to the quantum annealer. And this is our input as an example. So this is not fixed. It needs to be fixed. We need to find the delays for all of them. So we need to stack them together. Our regular method is called, I'm pretty sure many of you are familiar with it, is the cross correlations to find the delays and edit them. And with the best minimization or maximization for the cross correlation, this is the best image we can get. There we get a stack power of 0.08. And here we get, we're using the classical way, we get a stack power of 0.12. But the great thing about the quantum annealers is we can even reach more higher stacker power. Here we can get like 0.8, so they're more straight than they were before. And then we can get these delays from the final stack and apply, because we know this layer is straight, we get these delays and apply them to the input data that we started with. And after that, we can go back and stack again. So this is the first use case for the first geophysical case that was successful. As I said, it's a small use case, but it worked. It gave us something that the classical computer couldn't give us. Not by a far margin, but by a good margin nevertheless. The other problem that we focused on solving is called the quantum annealing sparse spike deconvolution. This is more of an inverse problem. And there are many solutions for it using classical computers, but we will show the results for both quantum annealers and classical computers. Okay, so here I'm showing Earth layers, and I'm showing a reflectivity sequence. So if the velocity, for example, for the second layer is slower than the first layer, your reflectivity will be negative. And if your velocity is the layer below is higher than the layer before it, it will be a positive reflectivity sequence. And what happens usually in the Earth, or the data we collect in Earth, is usually the convolution between the source that we sent to the Earth and the reflectivity sequence, which is the Earth layers to the left. And this is the seismic data that we have after we stack it together. This is, we receive this seismic data. And usually we always want to go back and get this, the reflectivity sequence, because this will help us get the layers. So this is what we see, what we get from the data. We know the wave we sent, and this is what we are trying to get back from the data that we have in the field. So the goal is to get reflectivity sequence from the seismic traces. So let's take a look a little bit at the reflectivity sequence. So first there is something we have called AI. It's not artificial intelligence in geophysics. It's acoustic impedance. It's an equation of rho versus V. So this is the density times the velocity. And to get the reflectivity from it, we just need to have two layers above each other, and we calculate the difference or the ratio of the acoustic impedance between those two layers. And so this equation can be also inverted to solve for the acoustic impedance through the reflectivity of the layers. It's a very simple equation, and geophysicists love this equation so much. So much. We use it everywhere. And so, by definition, we can go from the reflectivity sequence using the acoustic impedance and go back to the Earth layers. And so here is what happens usually. Okay, so we have seismic data. We collect this from the field. We need this argument or this minimization function. So we have the data, D, and we know our W, which is our wavelet that was sent to the Earth. And our R is the reflectivity, which we are trying to find. And we have a penalty term or a bias term that is useful that we can apply. In this case, it's the L0 norm, where we want to find the reflectivity. And once we find the reflectivity, as I showed, we have the equation that can take us back to the acoustic impedance that we want. So the goal is to resolve for this, is to solve this minimization problem and get the reflectivity from the seismic data that we have. So we go to this equation. We can see that this equation actually is also a Hamiltonian energy equation. We can easily convert it to a Hamiltonian, where we have the data and we're solving for R. And the great thing here that we can add is the L0 norm. This L0 norm, the bias term to the right, is very important. We cannot solve this using classical supercomputers because it's NB hard. It's very difficult to solve for. So the reflectivity term is very helpful because we can control the number, so the number or the count of the number of reflectivities, which we cannot do with classical computers. So when we solve it with classical computers, we'll get a trace, and maybe we get something that's more similar to a trace, not a reflectivity function. But with this term, the penalty term, we can control the number of reflectivities that we can get out of the solution for R. And here R, because as I said, this quantum computers only accept binary numbers, so it's the reflectivity is the amplitude multiplied element-wise by the binary subset of X in this case. And so let's solve for this, and let's see what reflectivity we can get. This is an example. So usually we solve in classical computers with the L1 lasso solver. We cannot go to the L0 norm. So this is an example of an image, an acoustic impedance image at the top of the predicted values using the L1 lasso solvers. And the one below is using the quantum annealer, where we could solve, because we know we have a good feel of how many layers there is in the Earth, so we can control the number of reflectivities. And using that penalty value or penalty bias, we can understand how many layers there are. We can give it like a good penalty term to solve for the equation, and then give us some kind of prediction of the acoustic impedance through that image. And so, as you can see, the image below, using the quantum solver, is more blocky, and this is what we need, compared to the lasso solvers at the top, where it has multiple variations. And these are the images that we currently work with in production, the one from the L1 lasso classical solver. And here I'll just show, this is the maximum, so this is the other issue with quantum, this is the maximum size we could input to the quantum annealer. So these are the seismic traces after the stacking that I received. So each line here, each vertical line is a trace that we need to invert to get the reflectivity. And there is two ways to do this. Either we do it using averaging, or we do it trace by trace. So this is an example where we do it trace by trace, and where I give a big penalty term. If I give a big penalty term, it means I want to have less reflectivities from my equation. And so this is how the reflectivity image will look like. So at each trace, we're here looking at the reflectivities from each layers. And the great thing is we can control these numbers. And if we do it using 1D, so this is only trace by trace, not taking them as an average image or a moving window. The first one was with the moving window. Here we're taking them trace by trace. And we get this predicted image. It's not, the issue when we do it as a 1D formulation is the result we get is usually, I would say, not continuous. So it's not that good of a solution. So we decided to go with the solution here to the left, which is inserting everything as a 2D window and moving on trace by trace. And I can show you finally, I can show you the results when we control or decrease. So when we decrease the regularization or the bias factor, the L0, for the L0 norm, you can see now the number of reflectivity increases, and this is similar to the solution that we get from the classical algorithm, which is the lasso algorithm. And this is when we do it for 1D. And this is great. Before, we could not control the number of reflectivities that we can get. So this adds something new or extra to us that we couldn't see before, or we couldn't get before. But at the same time, this only can be done on a very simple 2D image. And if it's done only on a very simple 2D image, it's not that very useful to us, because as you know, we collect, as in the beginning, tens and hundreds of petabytes. But it's a good solution, and it's something that is good to know for us. So when one day quantum computers become big, we are ready, and we know what problems that it can solve for us in terms of geophysics. Yeah, and finally, I would like to conclude, and so this is a summary and conclusions. So as I said, by finding problems in geophysics that can be mapped to the Hamiltonian energy problem, we can solve for these. And the difficult part is finding these problems that can be mapped to the Hamiltonian. We fail many times, but maybe for every 10 failures in geophysics, we find one that works, and which is great. And the addition of the L0 norm as an example for sparse spike deconvolution was useful for us to see something we didn't see before, like the reflectivities. And we can now have control on how many reflectivities based on the data that we had or the information we had prior. So thank you all for listening. Thank you. Questions?
For the interest of time, we'll probably take the questions offline, if you allow us.
Okay.
We are on a tight schedule.
Okay, no
but thank you so much. So our next speaker is Mr. Zia from AWS. He's a senior product manager in Amazon Web Services, joining us from AWS New York.
Hello, assalamu alaikum. So today we're going to be talking about Amazon's quantum computing journey. Tomorrow we're going to also be having a workshop. You can get more details after that, where we'll actually be diving into some of our quantum computing efforts, going hands-on, and allowing people who attend to actually play around with some of our quantum computing services and access some of the quantum computers that we have. So how did this journey actually start? So back in 2019, Amazon went to our customers, these large corporate enterprises, and we started asking, what do these customers want? And the 4 takeaways that we got when we asked about quantum computing, the first was companies really wanted to understand what quantum computing can do. There was a lot of ambiguity around this emerging technology. The second was, when do large enterprises actually go and engage in this? When does it make sense for them to get started? The third was, how do they build internal expertise? One trend that we noticed in AI was a lot of companies got left behind, and they didn't want to have that happen again. And the last was, how did they avoid massive upfront costs of buying these machines that year over year will be changing? And so it all started with hearing these use cases and diving in to what these industries were. And we've all heard of these before, logistics, machine learning, finance, energy, agriculture, and all of these Fortune 50, Fortune 100 enterprises all came with those 4 goals in mind. And so what we started doing was we called them quantum pioneers. These were those early companies such as JP Morgan Chase, Citibank, Airbus, or BMW that we started working with to see how quantum computing could impact their current industries and what were things that they could do in the future to take advantage of quantum computing. The QR codes, they'll be appearing throughout the PowerPoint, but this one is to our quantum computing blog. So it has a bunch of case studies and the companies that we've been working with. And what we noticed about these quantum pioneers was that they were the tip of the iceberg. Similar to what we noticed in machine learning was there were a plethora of AWS customers. Today, we have over 100,000 customers working on machine learning in AWS. And what we wanted to do was, how can we bring quantum computing to these customers? But it all started with those pioneers who were really curious about what quantum computing can do for them, how quantum computing is accessible for them, and how they can access it affordably. And so we came out with 3 different approaches. The first was Amazon Bracket. The second was the Advanced Solution Lab. And the third was our hardware efforts at the AWS Center for Quantum Computing. I'll touch upon each of these, but the first one we'll start with is the AWS Center for Quantum Computing. So this is based out of Caltech, where Amazon is building our fleet of hardware systems. It's based in Pasadena under the guidance of Dr. Oscar Painter. And our whole focus is how can we use quantum computing and build something in-house. We're using superconducting qubits, but the research that we have right now is focused on algorithms, but then also how we can improve the hardware. Currently, none of our devices are available, but we have a bunch of papers out that you can go and read. The second was, when we were talking to those quantum pioneers, one of the things that they kept asking us were, we want some actionable outcomes. We want to avoid the hype associated with quantum computing. What are some things that we can actually do? Again, understand when quantum will impact our business, and then informing business stakeholders what they'll be able to do with quantum. We launched Quantum Embark with 3 stages. The first was a level 1 module, a second was a level 2 module, and then the third was, the advanced one. The first one was focused at the CTO level, working with business stakeholders to understand what can quantum computing do for them, and the deliverable from that was a white paper, or is a white paper. The second is trials and POCs. So once you've decided what use cases you want to work on with Amazon, what are some ways that we can actually take these and start working on it with quantum hardware? And then the third was actually, deep dive into it further to better understand how can you integrate with HPC? How can you integrate with AI resources? And what we launched for each one of these was Quantum Embark to help companies get started, Amazon Bracket, which is the service I'll be talking about, which I'm the product manager for. And then the last was that Advanced Solution Lab, where you could work with Amazon scientists, Amazon researchers directly hands-on to not only collaborate in quantum computing, but also with AI and HPC workloads. And so Quantum Embark, it's a 12-week program. Each module is about 4 weeks, and it focuses on that use case discovery, training and enablement, and then deep diving into actually getting joint publications out. Some of these research needs for those quantum pioneers have spanned different applications areas. And the amount of time that each one takes to research takes a while. So if you're working on the energy sector and you're trying to refine unit optimization, that's a longer workload, longer engagement. But if you're working on molecular analysis, that's something that's a lot quicker. Can use simulators and quantum hardware to actually get going on that. But how do we actually access quantum computers? How can we actually get started with them? Because one of the things about quantum computers is not everyone can build them in a lab, and not everyone can afford to buy them. Before I go on to the next slide, this QR code is for the Quantum Embark program. So if you're interested, just shoot us an email, hello-quantum@amazon.com, or read more about it in our blog. And so that's where Amazon Bracket came in. This term of accessibility, which we started back in 2019, which really focused on how can we take this quantum technology, learn together, and provide access to people. And you'll start seeing this theme around access and really being able to democratize quantum computing. And so we worked with quantum hardware providers, which I'll touch upon in a second, who are third parties to provide quantum computing access. In the future, we hope that our own AWS quantum computers will be on Bracket for people to access. And then we started working with customers to provide this learning sandbox, a place where they could actually go and experiment. And this was all through one consistent experience. We started at the infrastructure layer. So working with QPUs, simulators, and then Amazon's high-performance compute. So that's GPUs and CPUs. Allowing customers to access these in hourly reservations, either through on-demand access, or for quantum classical workloads, providing them priority access. On top of the infrastructure, we started building platform tools. So SageMaker notebooks, these Jupyter notebooks that you ran locally, you could also run them on the AWS cloud. Through that, we developed a Python-based SDK, which I'll touch upon in a second, where you could access local simulators. You could do pulse-level access to computers from our partners. And you could do this all through existing frameworks, such as Qiskit, PennyLane, or even CUDA Quantum. Because why should you have to learn a new framework when there's already some pretty good ones out there? And then on top of that, we had those tools to enable those pioneers. So being able to work with our research scientists directly through a program known as Bracket Direct, access experimental capabilities. So QEra, which is one of the partners we work with, they have new features coming out, access them, at risk-free. Focused on working with executives at these large enterprises, and then really trying to craft this whole journey through the Amazon lens with a focus on the customer. And so what is this hardware that we have on Amazon Bracket? So at the moment, there's different types of topologies, ion traps, superconducting, neutral atoms, but we don't know which one is going to win out. And so the whole purpose of Amazon Bracket is to partner and provide you access to different topologies from different partners around the world. So on the Ion Trap stage, we have IonQ. They have their Aria and Forte devices. Rigetti, we recently launched their Anka 3 device. And then IQM, shout out to IQM in the back. We're working with them as well, and we have their system online as well. And these are all, quantum circuits, the ones that we know about. But then we're also working with different topologies, such as neutral atoms, similar to our folks at Pascal. I think someone was speaking about that yesterday. We work with QEra based out of Harvard and Boston, where they have an analog approach to quantum computing. And the whole purpose of Bracket is you write your program once in Bracket, in Qiskit, Penny Lane, and you can run it on all of these computers. In addition to hardware, we realize that simulation is also something that people are doing. And so not only do we have local simulators for noise modeling and state vector simulation, but we also have on-demand simulators. So the AWS cloud allows you to scale up your simulations. And so we have density matrix, tensor network, and state vector simulators that are available through the Amazon platform. In addition to that, you can bring your own simulator. So we have a quantum classical runtime that we've developed called Hybrid Jobs. And so if you containerize your own simulator, you're able to run that on the AWS cloud with Amazon Bracket, and then compare your results to either our simulators or some of the hardware. Recently, we also partnered with NVIDIA. I think it was around December or so. We added support for CUDA-Q, another existing framework that allows you to leverage not only CPUs and GPUs, but also with Bracket Hybrid Jobs, run those workloads on quantum computers directly. How do you access Amazon Bracket? So it's a classical AWS service available through the cloud. So you as an end user can take two approaches. You can either do a quick pip install, run it locally, install the SDK, and start programming directly. Or when you log into the AWS Management Console, you can go ahead and access it through the cloud. And so let's actually talk about how this looks. So simple SDK, if you're installing it locally, pip install it. If you go to the AWS catalog, you're able to access it, just click on the tile and access it directly. And so how does it actually look? How does it work? Pretty straightforward. You import your Bracket SDK. You go ahead and select your device, any of those hardwares or those simulators, input them as an ARN, so an Amazon resource name, create a simple circuit. In this case, we're just using a Bell circuit. And then you say, hey, I want to run this Bell circuit on 1,000 shots. Existing quantum framework that uses shots, tasks, jobs, same terminology. And then you can actually get your results. You can get your results stored in an S3 bucket. You can get them locally. However you actually want them, they're available to you. This SDK is complemented with that hybrid jobs feature that I was telling you guys about. So yesterday we heard this theme around quantum and classical and how it's increasingly becoming prevalent. We have quantum computers, they're experimental, but then today we have GPUs and CPUs. How can we actually ensure that they're working together? And in the future with HPC. So we've built out this quantum classical runtime for you because quantum computers aren't good at everything. There's certain use cases where quantum and classical must work together, and the algorithms that you run switch between the quantum resource and the classical resource. But why should you have to do all of that orchestration yourself? And so the way hybrid jobs is essentially built is you take your program and you containerize it with a simple Docker container. You have your parameterized quantum circuit in there. You input your classical parameters. You get your outputs from a QPU. And basically, there's a nice animation here. So the QPU is really good at solving a specific question. Then it passes it off to that CPU. And it's like, hey, maybe you're better at doing something else. CPU goes and it's like, hey, this is pretty easy. Gets your answer. Then it goes back to the QPU and it's like, okay, I get it. And so this whole runtime, this back and forth, is what hybrid jobs is essentially doing for you. So you have your program that you've written. It has classical elements. It has your quantum elements. Containerize it in that Docker container. Submit it to hybrid jobs. and we'll take care of the optimization for you. You can select your GPU resource and any of those QPU resources directly through a GUI interface or through the Bracket SDK. Again, just reiterating some of this stuff where, CPUs and QPUs and GPUs as well act as co-processors. So you input your new parameters, you run it on the QPU, you get your results, you go back, and you have this iterative loop that you can run across devices. Let's say you run it on the Rigetti device, get your results, but then you want to compare. How does this actually work on an IQM device? You simply swap out the ARN, and you'll run that exact same program on the exact same device. We take care of all of the compilation for you. Again, as workloads become more and more advanced, the interlock between CPUs, GPUs, and QPUs will become ever more prevalent. And so Hybrid Jobs essentially provides you this interface, this runtime interface, to take care of that for you. The three main things with Hybrid Jobs is, again, that convenience. The second is actually insights. So it's not a black box. In real time, you're actually seeing the results as they're coming through, and you can have them stored wherever you want. And then the last is about optimizing performance. Not only do we give you priority access to these quantum computers and our GPU resources, but you get to have them, again, prioritized. The next thing, in addition to Hybrid Jobs that we offer through Amazon Bracket, is this program called Bracket Direct. One of the things that we were hearing from our customers was, hey, it's great that we can access these computers on demand, but how can we actually get reservations? How can we book hours on these quantum computers? And so the three things that we enabled with Bracket Direct were dedicated private access. If you want access to a QPU for 1 hour or 5 hours, we can give that to you. The second was connecting with specialists. Free office hours, directly connecting with either Amazon scientists or people who are working at the quantum computing companies that we work with. One-on-one coaching sessions, all included, accessible completely for free today. And then the last was that new capabilities that I was talking about. So with our hardware providers, QEra is one that comes to mind. They have different approaches in neutral atom quantum computing. Some people want larger geometries. Some people want local detuning or tighter geometries. All of these early access capabilities are available at no extra cost to our customers. They're pre-GA features, so we have to work with our scientists and you directly, but it's something that we also have started enabling across our suite of devices. This is just a screenshot of our console. So you can see when you go into the Amazon Bracket or AWS service and you go to Amazon Bracket, you'd be able to see Bracket Direct, our free office hours, any of the quantum computing partners that we work with. And then in the left-hand side, you'll see we have a dashboard, access to the devices, an algorithm library, and a whole bunch of other things that you can access. How do you get started with Amazon Bracket if you're not familiar? So we have a couple ways you can engage. One, you can directly go to the Amazon catalog and start accessing it yourself. The second is we've developed some educational materials. A lot of people are curious about quantum computing or Amazon Bracket. And so we launched a badge. Working with our corporate certification group, we have around a 3-hour course. It's broken up into 2 segments that you can take. After that, you take a quiz. You have to score a certain amount, and then you get this Amazon badge. The second is stay up to date with what we're doing, which is our quantum technologies blog. We have access to different publications that we put on there. When we're working with those quantum pioneers, or we have joint case studies, we end up posting them on our blog. And then the last is, if you're curious about what algorithms we have, you want to see, direct code examples, go to our GitHub repo, look at those examples. We'll be touching upon some of those in our workshop tomorrow as well, really providing that hands-on experience. But these are the 3 main ways. I'll be available for questions at the end, but yeah, feel free to send me an email. It's just my initials, or connect on LinkedIn. I'll go back to the QR codes in case people want to scan them. But
Okay.
Thank you, Zia. And I think Zia will be available outside this room for more engagement and for more questions. So I think we are off for the lunch break. We are generous. We're giving you 2 hours of break. So inshallah, we'll resume our agenda at 1:30. Okay, so the agenda got updated a little bit. So we pushed the starting our afternoon agenda at 1:30, inshallah.
تيست مايك وبنستخدم تيست صوت مايك غير كده.
test. Check. 3, 2, 1. Test. Three, two, one. Check. Test. Three, two, one. Check.
الرحمن الرحيم. تيست مايك.
Assalamu alaikum wa rahmatullah. Hello everyone. I hope you had a healthy lunch. Now we have I want to introduce our next speaker, Dr. Professor Matteo from Waterloo University. He's a world expert in quantum error correction and superconducting quantum circuits. He will give the talk now. Okay, we'll wait about a minute. I will go outside and ask you all to come.
It doesn't matter. That's old.
Okay.
Let's keep that.
Okay.
You can reintroduce them if you want, as you wish. Let's do it another. I think they're just coming in.
Hello? Hello? Now we're gonna. Okay. Hello? Now we're gonna resume our sessions with Dr. Matteo from Waterloo. He will talk about understanding, mediating, and using dissipation superconducting quantum circuit. Please give us a big applause now. Okay.
All right. Good afternoon, everyone. So thanks for the introduction, and thanks KFUPM for inviting me here today. So understanding, mitigating, and using dissipation in superconducting quantum circuits. So in this talk, there will be two parts in this talk. In the first part, I will tell you how we understood and mitigated dissipation in these devices. And in the second part of the talk, so in the first part of the talk, dissipation is going to be our enemy. And in the second part of the talk, dissipation is going to become our friend. So I will tell you how it's possible to use dissipation to generate interesting quantum mechanical phenomena. All right, so let's begin with some introduction. In fact, considering that some time has passed already since Professor Siddiqui's and Rao's talks yesterday, I think it's worth going over some basic materials about superconducting quantum circuits one more time. And so let's begin with the simplest superconducting device we use in our labs, which is an electrical resonator. This can be implemented, for example, as the parallel connection of a capacitor CR and an inductor LR, as in this sketch here. So in this case, the classical potential energy of this device is a quadratic potential, so a very simple harmonic oscillator. And so if you were to measure the amplitude of the impedance of this device, we would measure a Lorentzian curve, which is centered at the transitional resonance frequency FR of the device, which is inversely proportional to the square root of L times C. And so typically we made these devices out of aluminum, which when we cool it down to below approximately 1 Kelvin, it becomes superconducting. Although it is superconducting, there is still some residual loss, some conductor loss due to residual passive particles. Although this is not the main source of dissipation in our devices. The main source of dissipation in our circuits is actually the electric loss in the capacitor, which can be modeled as a resistance in parallel with this capacitance. And so in this case, this resistance leads to a finite width of the Lorentzian, which I have up here. And so this width, which results in a full width at half maximum, which is approximately there in a logarithmic scale, allows us to define the internal quality factor Qi of this device, which depends, of course, on R. So typically, we engineer this resonator so that the resonance frequency is about 5 gigahertz. And so when we cool them down below 50 millikelvin, they become quantum mechanical harmonic oscillators. And so they are represented by an equally spaced ladder of states, 0, 1, 2, etc., where the separation is proportional to the frequency FR. What about qubits? Qubits are a little bit more complicated. And so a typical qubit in our case is enclosed in this blue region below here. And so once again, like in the case of resonator, it comprises a capacitance CQ in parallel with an inductance. However, in this case, the inductance is realized by means of a Josephson junction, a cross down here. In fact, in our experiments, we typically use a couple of junctions forming a superconducting loop, which we call a squid loop, a superconducting quantum interference device. So this allows us, in fact, to change the frequency of the qubit, the characteristic frequency of the qubit, the transition frequency, FQ. So because of this nonlinear inductor, now the potential, instead of being quadratic, is quartic, like here. And so the energy spacing between the energy ground state G, the excited state E, and the other states is not equal anymore. So from G to E, we have a frequency FQ and a slightly different frequency from E to F. So in this specific device, which is called an X-Mon-Transmon qubit, this potential is quartic, and so the device itself behaves as a slightly nonlinear resonator or anharmonic oscillator. Okay. So now you may notice a few more circuit elements in this diagram. For example, the inductor below here, which allows us to thread a flux in the squid, therefore allowing us to change the frequency of the qubit on demand during the experiments. You can also notice a capacitor up here, which allows us to apply micropulses, which eventually make it possible, for example, to prepare the qubit in any arbitrary linear superposition of G and E. And finally, we can couple this slightly nonlinear oscillator, which is our qubit, to a linear oscillator like the one I've shown in the previous slide. And in this case, the nonlinear oscillator effectively behaves as our measurement apparatus, which eventually allows us to measure the probability for the qubit to be in the excited state P of E. Okay, so we can perform an experiment, a simple experiment like the following. We begin applying a flux here through this inductor. This allows us to change the potential landscape from this configuration to this configuration so that the spacing between G and E now is, for example, larger. We can then apply a micro pi pulse through the capacitor over there, which allows us to energize the qubit to the excited state. And finally, we measure P of E as a function of time, a function which decays exponentially with the time constant T1, which is called the energy relaxation time of the qubit. So this type of experiment, the one I will be focusing mostly in this talk, with some caveats, which I will explain later. However, before doing that, I think it's worth looking at some actual photograph, actual image of our device. So the top right panel over here is a photograph of one of our devices. And each cross corresponds approximately to a qubit. And so if we zoom in into one of these cross regions, we can, by means of an optical microscope, we can more directly observe this aluminum island in light brown, which actually is the capacitance CQ of the qubit. If we want to observe the Josephson junctions, the nonlinear part of the qubit, we need to further zoom in by means of a scanning electron microscope, like in these pictures here. And here we can actually finally observe the Josephson junctions, which are nothing but a sandwich between two aluminum leads and an aluminum oxide barrier in between. Okay, so in this figure, as I said, the light brown represents aluminum, whereas the dark brown represents the silicon substrate on top of which we deposit this aluminum, which forms our qubit. Okay, if we want to understand the origin of the energy relaxation time, T1, of our devices, we can, for example, take a cross-section along this red line, okay, and then look at this laterally. And so when we do that, we can understand dissipation due to dielectric materials. Okay, so that's what we see, in fact, by doing that cross-section. So now here in green, we have the silicon substrate. In blue, we have the aluminum deposited above it. And we know that silicon and aluminum, when exposed to air, develop native silicon and aluminum oxide, respectively. These are amorphous dielectric materials, and it is well known since the 70s that amorphous dielectric materials contain defects, and these defects are what actually eventually impact our energy relaxation time T1. So that's what we need to understand. Okay, so in fact, our devices are completely encapsulated within these amorphous dielectric materials. And so to understand them, we can consider the window in red over there, which now I rotate down here, and I perform high-resolution tunneling electron microscopy, like in this picture. So now The structure here on the left is the lattice associated with the silicon. The structure on the right is the lattice associated with the aluminum. And this whitish region in between is silicon oxide, where the defects are located. That's what sets our T1 time. So we can perform some EELS, which is electron energy loss spectroscopy, in order to find the elemental composition more in detail of this in that window. And so this window here is effectively the same as this, but with these EELS in it. And so in green again, we have the silicon substrate. In blue, the aluminum. And the whitish region, one more time, is the silicon oxide, which, as you can see here, is approximately a nanometer in thickness, 1 or 2 nanometers in thickness. OK, so now the origin of the defects, which are in these amorphous dielectric materials, is something which has been debated for half a century and is still under debate. So if I were to bet my money, what is the origin of these defects? So many people think it could be dangling bonds. Other people think it could be electrons. If I were to bet my money, considering the experimental evidence I'm about to show you, I would think that is heavy oxygen atoms, which are tunneling inside this dielectric material. So it's a tunneling of oxygen atoms. So in fact, if we were to further zoom in into the silicon oxide region, we would be able to see oxygen atoms pivoting between a pair of silicon atoms from a left configuration to a right configuration. So atomic tunneling, which is a quantum mechanical phenomenon, leads to these two-level state defects, which are this atom of oxygen pivoting between two silicon atoms. Okay. So now we think that the origin of defects is tunneling of atoms. How can we mathematically model this system? One simple model is based on a double well potential, as shown here. And so in this case, oxygen is a particle with mass m, 16U in the case of oxygen, obviously. If we throw this particle at the bottom of one of these wells, it begins oscillating. The frequency of these small oscillations, which is called attempt frequency, is omega naught. And typically in our experiments, the matched data is approximately a gigahertz. Furthermore, these double well potentials are asymmetric, and the asymmetry is given by this quantity delta. The distance between the left and right wells, which are the two possible positions of the oxygen, is on the order of the interatomic distance, so approximately a few angstrom. That's the bond length. And finally, most importantly, the oxygen particle with mass m can quantum mechanically tunnel through this barrier, which has a height v, with a tunneling energy delta naught that can be estimated with WKB approximation. And of course, it depends on the distance d, the mass m, as well as v and omega naught, the attempt frequency. Okay, so effectively, a two-level system is nothing but an unwanted qubit which interacts with our resonator qubit, taking energy from it. And so the Hamiltonian is that of a qubit, if you want. Okay, so now this one is a reasonable model for a single TLS. Of course, at this silicon oxide interfacial region between the silicon substrate and the aluminum films, there are obviously many of these defects. And so in order to understand how all these defects interact with our resonator qubit, there is a model which was developed in the 70s mostly by Philips. This model is called the standard tunneling model, or STM. So the STM hypothesizes that our resonator qubit, which here is represented by its states at 0 and 1, and by some electric field ERQR for resonator qubit is very similar, the concept. So this is our resonator, the electric field of our resonator qubit, and this device interacts, according to this model, to many of these TLSs. In reality, in our experiments, we think they're about 1,000-ish. And so the interaction is an electric dipole interaction. So there is the electric field of the resonator qubit, and then the model assumes that all these TLSs are effectively electric dipole moments. And so P dot E is the interaction energy between them, which leads to the coupling strength G between the qubit resonator and the various TLSs. So these TLSs in blue, in order to actually interact with our resonator qubit, they must have a resonance frequency which is comparable to that of the resonator qubit, which, as I told you, is about 5 gigahertz. So any TLS, any defect which has a frequency between 1 and 10 gigahertz or so, will interact semi-resonantly with our qubit. And so these TLSs are particular because their energy, H times the frequency of these TLSs, is larger than the thermal energy KBT when we operate the system at 50 millikelvin or lower. And therefore, at the beginning of the experiment, all these TLSs are in their quantum mechanical ground state. And that's why we call them quantum TLSs or QTLSs. Okay. The model, the STM model, further assumes that all these interactions are independent from each other, and it further assumes that there are not TLS, in this case QTLS interactions. This is important for in a few slides from now. So the Hamiltonian, the interaction Hamiltonian that describes the interaction, of course, depends on G, the electric dipole coupling strength, which I just discussed a minute ago. Sigma X is the Pauli matrix, which represents mathematically a QTLS. Tensor with A plus A, which has bosonic operators representing the electric field in the resonator or qubit. Typically, they are used for resonators, but a qubit, in our case, is a slightly nonlinear resonator, so they're still valid operators in that case. Now, that's the unitary, that Hamiltonian will lead to a unitary evolution. However, if we want to understand the dynamics that take place between a resonator or qubit and all these QTLSs, we need to write down master equations in, for example, a Lindblad form. Why do we need to do that? Because each of these QTLSs as a qubit is characterized by its own energy relaxation time, T1 QTLS, which in the case of QTLSs depends on the interaction between each QTLS and the acoustic phononic modes of the dielectric materials which they are part of. So basically what happens is that if I excite this resonator or qubit, this excitation will swap due to G with one of these QTLSs. Each of these QTLSs, once excited, will decay phononically in the environment they're part of, and that's a lossy channel. Now, if we were to do this math, so in fact we need to solve approximately 1,000 independent Lindblad master equations to understand what's going on, what are the dynamics of this system. So if we were to solve this problem, for example, for a resonator, we would obtain the most important equation of the STM, which tells us that the internal quality factor Qi, or better yet, the inverse internal quality factor 1 over Qi, is inversely proportional to the root of the mean number of photons we use to illuminate the resonator, to measure the resonator. So you can think of this number of photons as the pump power we use to measure the resonator. When this pump power is low, for example, the mean number of photons is approximately 1, so 1 excitation. So this excitation will excite the resonator or qubit, but at the beginning of the experiment, all the QTLSs will reside in their quantum mechanical ground state. And so they are allowed to swap information with the resonator or qubit. Once that happens, then they, on their own, decay, and that's the lossy channel. Okay. So now that we know that, this regime, in fact, we call it the quantum regime, because in quantum computing, typically we use low excitations. Okay? So in this case, the internal quality factor is strongly limited by TLS, so it's TLS limited. On the other end, when we apply 1,000 or tens of thousands of photons, what they do, they will saturate eventually all these QTLSs, making them effectively inactive, so they cannot interact anymore with the resonator or qubit because they are saturated, they already have information in them, they cannot exchange any further information. Since they are saturated in this high power configuration, we end up having an internal quality factor which does not depend anymore on the QTLSs, which are effectively turned off. And so we would have a much higher quality factor Qi. And if we were to interpolate the low power quality factor with the high power quality factor, we would obtain this curve, which is called the S curve of the STM model. And that's what we will measure in the next experiment. In fact, let's perform the first experiment here. So the top panel, top left panel, panel A, is exactly what I showed you before, a few slides ago. It's an unprocessed device where we have aluminum on silicon without any cleaning of the silicon substrate. So there is the silicon, a couple of nanometers of a nanometer or so of silicon oxide in the interfacial region. However, we can clean these devices, for example, chemically as in B. Chemically, the way we do a chemical clean is we take the silicon substrate, we dip it in HF acid, and then as soon as possible deposit aluminum. So we obtain a cleaner surface. we can obtain a similarly cleaner surface by preparing the silicon substrate in ultra-high vacuum and then heating it up to 800 degrees Celsius, at which temperature oxygen desorbs and so resulting in a clean surface. Or we can apply, of course, we can use a combination of both cleaning methods, resulting in the best interface. And in this case, if we measure the internal quality factor as a function of the number of photons that we use to measure this resonator, of course, we measure the S-curves I described in the previous slide. And at the bottom here in the quantum regime, the quality factor gets higher and higher and higher with the cleaning procedures, as expected. And eventually, in the best case scenario, in these particular experiments, we touch approximately 1 million of quality factor in the low power regime. Now, these curves are great because they corroborate the STM, the standard tunneling model. However, they are not sufficient to explain many other features of our devices. In particular, suppose that we were to measure the inverse internal quality factor as a function of time. So I remind you that to measure our quality factor effectively, we need to measure the Lorentzian curve as shown in the beginning. And so to feed it, and it takes about a minute to do that, and then we measure minute after minute back to back for, let's say, 40 hours, 40, 50 hours. And we plot this obtaining a time trace like the one shown here. So let's focus now on the blue time trace, which is in the quantum regime that is for low power. And so if we, in certain time windows, like in this time window here, the quality factor, although a little bit noisy, is actually rather stable. However, there are different time windows, like the one here, where the quality factor undergoes wild jumps. These jumps cannot be accounted for by the STM, the standard tunneling model. To understand these jumps, we need to develop a more refined model, which is called the generalized tunneling model, or GTM, which in fact was developed only about a decade ago. So the GTM hypothesizes a new category of TLSs called the TTLSs, thermal TLSs. Okay, what is this new category, this new class of TLSs? Okay, as before, we have our electric field of the resonator or qubit coupled with G to 1,000 QTLSs. These QTLSs, they have approximately the same frequency as the resonator or qubit. Each of these QTLSs, in turn, is hypothesized to interact with a few TLSs, whose frequency will be approximately between 0 and a few hundred megahertz. And when we operate our devices below 50 millikelvin, all these TLSs at this low frequency range, they will have an energy which is less than the thermal energy. Therefore, they will be thermalized, and that's why we call them TTLSs, thermal TLSs. So the GTM additionally assumes that there is an interaction between TLSs, in particular between QTLSs and TTLSs. And this interaction is given by an interaction strength U, which depends inversely by the distance R between adjacent TLSs, which is on the order of a couple of nanometers. So this interaction, which was neglected in the STM, actually is very strong because of the spatial distance, which is small between these TLSs. So at this point, what happens is that these TTLSs, despite the fact that they are thermal entities, so practically a classical device, if you want, a classical entity, classical system, they can still be represented as a double well potential. However, in this case, the oxygen does not go from left to right by quantum mechanical tunneling. Instead, there is a thermal activation which allows it to go over the barrier of height V. So in this process, as a rate, is a stochastic, a random process characterized by a rate gamma, which depends on the ratio between the height of this barrier and the thermal energy. Effectively, this is random telegraph noise. So let's recap what's happening here. So we have a bunch, where the qubit or resonator coupled to 1,000 QTLSs with coupling G, electric dipole coupling. Each of these QTLSs, in turn, is coupled to a few, as I will show you in our experiments. We think that is about up to 10 of these TTLSs. These TTLSs are thermalized and undergo stochastic jumps, so stochastic events. So if we look at this now backward starting from the TTLSs, we have a stochastic jump on the TTLS, which because of U gets transferred into the QTLS, resulting in a stochastic jump of the frequency of these QTLSs, which we indicate here as delta F minus plus. In turn, these QTLSs are coupled to the resonator or qubit, and therefore the stochastic jumps transmit eventually all the way to the properties of resonators and qubits. And that's the origin of the jumps which I've shown in the previous slide. So in the simulations which I'm about to show you, since there is some stochasticity in the process, the GTM assumes certain distributions from which to pick parameters such as delta, delta naught, and the dipole moment P. So now let's perform a tiny bit more refined experiment. In this experiment, instead of using a resonator, we use a qubit. And why do we use a qubit? Because we can tune its frequency, as I've shown you. For a resonator, we couldn't do that. So let's focus on the top row here, where on the x-axis we have the qubit frequency, which we tune by applying a flux through the squid loop. And on the y-axis, we have time up to 40 hours, in this case, approximately. You may notice this we call spectrotemporal charts. And the spectrotemporal charts unveil a number of features, which, in fact, we wouldn't want to have in a quantum computer. You would like this to be flat and as high as possible. Because, in fact, in color code, we have the energy relaxation time of the qubit, so you would like these plots to be as yellow as possible all the way. Okay? But there are many features. And so even though there are many features, we can pinpoint 3 specific prominent features. The first one in magenta is band-limited diffusive, as in this magenta box or that magenta box. So this is a sort of 1 over f noise kind of region where this pixeling happens in a range of a gigahertz or so and throughout the whole time of the experiment. But they're small, okay? The second type of noise is fast, narrow band telegraphic noise. This is the easiest one to see in these experiments and is really abrupt and wild. So it happens at approximately 1 single frequency. You can look at this frequency here. And the T1 of the qubit is extremely good until a certain point, and then it becomes extremely bad. And then eventually, after some time, randomly becomes extremely good again, and so on and so forth. So this is the most dramatic type of noise we have in these devices. And finally, we have a slow wideband telegraphic noise, which is sort of similar of the one I just described, but it happens through the entire frequency spectrum, like, for example, this line up here, or this line there. So in other words, until a certain point, T1 is good across the whole frequency range, and then it becomes bad and good again across the entire frequency range. So can we perform a simulation based on the generalized tunneling model at GTM that allows us to reproduce these features? The answer is yes. To do that, we simulate a single qubit coupled by means of 1,000 or so independent Lindbladian master equations to a QTLS. Each QTLS is stochastically coupled to a few TLSs up to 10. And so when we do that, we then randomly generate all the parameters according to the distribution I've shown you before, and using the parameters I've also shown you before, we post-select and we obtain these plots down here, which quite nicely reproduce the features, also in magnitude, of the experiments. Now, let me make a note here. The experiments take 40 hours. So it takes 40 hours to measure one of these spectrotemporal charts. However, the simulations take just a couple of minutes for each of these charts. So the simulations allow us to span a much longer time range, and that's why we need to perform hundreds of simulations and then post-process to get the ones which actually reproduce these results. But the nice feature is that using a fixed set of parameters and the distributions and theory, which is due to the GTM, associated with the GTM, the generalized tunneling model, we can reproduce also the amplitude of these plots, which means we are effectively making a sort of manual fit, if you want. Now, this may seem sort of easy, but actually it's a monumental effort that took my best grad student 2 years of their time to actually make these simulations, because it's fairly complicated, okay? So it's not that easy. And in fact, we were not the first, of course, to make this experiment. It was Paul Klimov at Google, the first to make it, but we were the first actually to explain it with a model. Okay, so this is the last slide of the first part of the talk, and then I will move quickly to the second part. And so if we want to understand a little bit more in detail all this model, we can focus on a single QTLS coupled to a bunch of TTLSs. That's what's happening in this panel A here. And so in the first case, we are assuming a single QTLS, which is coupled in order to reproduce the diffusive noise, so the 1 over f noise, as expected, is coupled to approximately 10 TTLSs, because many TTLSs behave as an ensemble, result in a sort of ensemble effect, and so lead to this sort of diffusive pattern. Whereas if you want to observe a more telegraphic kind of noise, you want just a very few TLSs, 2 or 3. And if you want to observe the wideband telegraphic noise, again, you want only a couple of them. However, the rates must be smaller and the coupling must be must be stronger. And so then we propagate the single QTLS, many TTLS simulations with Limbladians to the coupling with the qubit, and we again reproduce the features we have seen in the plots before. So that's how we can make a manual fit if you want. The last point I want to make about the TLSs is that the standard tunneling model assumes that the TLS distribution is constant for the entire frequency spectrum. On the contrary, the GTM assumes that there are much fewer QTLSs at high frequency than TTLSs at low frequency, which makes sense, because if we have 1,000 QTLSs and each of them is coupled to up to 10 TTLSs, the density of TTLSs must be much stronger. So this allowed us to shed some light on the distribution of density of TLSs, which was rather unknown up until that point. Interestingly enough, even though they have not done a manual fit like we have done, Paul Klimov's, so Google result, confirm our numbers here, even though they had done this confirmation in a sort of qualitative fashion, whereas we actually solved the simulations. Okay, so at this point, let me just show you. This is all the literature we have generated in my group about this topic. And so, in particular, in the last couple of results from the past 2 years or so, we extended our measurement time to more than 1,000 hours. So we measured basically for a few weeks continuously these devices. All right, so at this point, we managed to understand and to create rather high-quality devices. So there could be a couple of possible next steps. So one possible next step would be to begin building a sort of a small, medium-scale quantum computer. The other possible next step would be to use these high-quality devices to investigate some basic fundamental science. And I will focus on the latter option. So using dissipation. So now dissipation is going to become, after all this spiel about dissipation is bad, now we're going to use it as an active means. So what arguably is, in my opinion, the best example where dissipation is actively being used to generate, to result in interesting physical phenomena is synchronization. So synchronization is ubiquitous in all possible realms of nature, from the synchronous blinking of the fireflies to the infamous wobbling of the London Millennium Bridge. And so this is actually already quite interesting because the bridge effectively behaves as a beam, so as a mechanical resonator. And what happened when they opened it is that people started to eventually, after a couple of hours, walk all together left and right, in a left and right motion, like if there was a music being played and they were dancing at this music. There was no music. The music was actually the mechanical vibration which were transmitted between the feet of the people walking from horizontally across this beam, okay? So, and it almost destroyed the beam, the bridge. So it's kind of pretty important. In my opinion, though, the best example of synchronization is Christian Huygens' 17th century pendulum clock synchronization. So it turns out that in the 17th century, navigation had some serious problems in terms of precision of measuring time. So the time measurement on ships and boats was really bad because of the rocking of the boat. And so Huygens came up with an idea to resolve this rocking issue, which was influencing measurement of time, developing the pendulum clock, which you can sort of decouple from the rocking of the boat. But then, as it turns out, he was also a good engineer, and he said, okay, let's not put only one clock. Let's put two clocks for redundancy. This was actually interesting because it appears that he had one of these constructions in his home, and so he had a couple of clocks, pendulum clocks, coupled to the same wooden beam, and he noticed that regardless of the initial state of the clocks, eventually these clocks began oscillating synchronously after some time. He thought originally that it was perhaps the air between the clocks that was resulting in this synchronous motion, but now we know that it's not the air, is the mechanical vibration, so the acoustic vibrations through the wooden beam which connects the two clocks, acting as a dissipative environment connecting effectively the two clocks, which become synchronous after some time. So a pendulum clock is nothing but a simple harmonic oscillator, using the small oscillations of a simple harmonic oscillator. So it's a resonator. So can we implement something like this using our electrical circuits? Obviously, yes. And the simple way to do that is by means of two clocks, two LC resonators. R1 and R2 are the local resistances of this resonator, the one I described in the first part of the talk. We want still to keep this low to unveil interesting phenomena. But then the key is to connect them. Yeah, here I also put LNC for generality, but the key is R12. So we want to connect the two clocks, the two resonators, by means of a resistor. Okay, so just a resistor, in fact. And so a dissipative environment connects these two clocks. So as I already advertised in the first part of the talk, typically we work at about 5 gigahertz. So this classical synchronization electric circuit becomes immediately a quantum mechanical system as soon as we operate these devices, as we do, below 50 millikelvin. So we can immediately move from a classical synchronization scenario to a quantum synchronization scenario. And so what we can do in the quantum synchronization case, we can prepare the left resonator in a G plus E superposition and the right resonator in the ground state G, let evolve in time and measure, in fact, the quantum mechanical charge Q1 or 2 on the capacitor C1 and C2, and plot this as a function of time. When you do that, let's focus on the top row. We see these plots, particularly the zooms, the zoom ins B and C. In B, we can see this is the beginning of the evolution. The two charges are completely oscillating in asynchronous fashion. But after some time, which depends on the resistance that connects the two resonators, R12, we reach perfect synchronization. So typically, people want to connect to make a C0 gate qubit by means of a capacitor, which is purely reactive, not dissipation. We want to connect them on purpose with a resistor. Okay, so Irfan, I don't see him around, yesterday said that the resistance cannot lead to entanglement. I disagree, because as I will show you, it does lead to entanglement. So the top row is for a zero detuning, which means I'm assuming perfect resonance between the two resonators and a very high quality factor, the one which we actually typically measure. But to verify whether some imperfections like a detuning or a lower quality factor will still lead to synchronization, we perform a simulation also with these parameters. And in fact, even though there is a little bit of decay, we still reach perfect synchronization under improper conditions, also including these imperfections. Now, together with Noah, who is actually here in the audience, we developed a theoretical framework which is based on what I call the Kirchhoff-Maxwell rules, and leads to a representation of the quantum mechanical system here in the Heisenberg picture, which is the most native way to introduce dissipation, in my opinion. So we have independently done this theory in this framework. However, other people have solved similar problems in the Schrödinger picture using Imbladian master equations, like in this work by Cattaneo et al. And what they have done, more than us in that theory, is that they not only show that there is synchronization, but they also measure negativity, which is the color bar here, which is a measure of entanglement between the two resonators in presence, again, of some imperfections of detuning, and depending on the coupling strength, in this case, the resistance R12. And so what this plot tells us is that actually, synchronization leads to entanglement. There is significant entanglement once the two resonators are perfectly synchronized. So this is a beautiful example of dissipation-induced entanglement. A resistor can actually lead to entanglement. And that's what we are attempting to show this in the lab in the foreseeable future. In fact, Noah is already working on the characterization, the fabrication and characterization of one of these resistances. For example, we are cooling down currently devices similar to this one, where a capacitor, inductor, this is a resonator, and we put a gold film resistor in between. So we are at this point in time characterizing this resistance at micro frequencies. And I think before the upcoming APS March meeting, we will have data showing this characterization. Classical synchronization, before, just with simple coherent states, I think we can do it by the summer of this year. Quantum synchronization with qubits in the next 1 or 2 years. So that's the plan we are aiming at. This seems a great one-off experiment for Noah's PhD thesis. However, the reason why I want to study this goes beyond that. And to do that, I still have 6 minutes, right? And to do that, so first of all, I'm not done yet, so let me step back for a second and let me thank, before I show you the outline of my plan here, my team, in particular, Jeremy Bejanin, with whom I developed the theory and experiments on TLSs, and Noah Gorgichuk, with whom I'm developing the theory and experiments on the quantum synchronization. Also in the audience here, we have Christopher and Mohammed. You can interact with them during this conference. So why do I want to study quantum synchronization? To do that, we need to go back to the 1950s, when two English medical doctors, Hodgkin and Huxley, developed the first mathematical model of a brain neuron. So a brain neuron comprises a cell body, a bunch of dendrites, and an axon, which is actually the transmission line along which we can transmit signals. The signals in our brain get transmitted, and many of these axons many of these neurons together form our brain, our neural network, which is the neural network, which is our brain. To understand this model, we need to zoom in into the axon. And so then what we see here, we see a lipid bilayer, which is these gray dots. This lipid bilayer separates an extracellular space from an intracellular space. Okay, so these spaces are characterized by some solutions of ions like sodium or potassium. And the electric imbalance between these solutions in the extra and intracellular spaces results in a charging effect on this lipid bilayer, which can be modeled with a capacitance Cm. That's the first element of the model. The lipid bilayer is also characterized by gates, which allow ions to move through the intra and extra spaces. And so the driving force is the electrochemical gradient, which can be modeled with a battery. And the gates themselves are highly nonlinear gates, which can be modeled with a sort of resistance that depends on the voltage drop on the lipid bilayer, as well as time evolution. So we know that these neurons effectively are a sort of also lead to memory. And so we know that memory in physics is typically given by a hysteretic behavior. So we expect, so the model predicts that this nonlinear resistor should actually be some hysteretic devices. And of course, there are regular resistances and some current source. I will not go into the details of what that is. But the key element here is this nonlinear resistor. In fact, Hodgkin and Huxley, who won the Nobel Prize in Medicine for this model, they didn't actually come up with the circuit. The circuit was, they only wrote down a number of nonlinear differential equations. So in order to derive this circuit, we had to wait until Leon Chua in the 70s, who proposed a device which actually does exactly the job of the hysteretic behavior job that I was talking about. And this is called a memory resistor, a memristor. The first experimental implementation of a memristor, and so here I have a chart with resistors, ohmic around zero, capacitor inductors, which are the typical reactive loops, and a memristor. These are IV characteristics, and so which is this hysteretic behavior. The first experiment classically to perform a memristor was done in 2008 at HP Labs. Since then, HP, Intel, and other companies have been developing a non-conventional classical computer called neuromorphic computer with good results already. So this is the key element to implement this Hodgkin-Huxley model. This has been done classically. Can we do this with superconducting devices? We can. There are several proposals. The first one of which is from Max de Ventra's group, who is the biggest expert probably on memristor at this point in time, together with Chua. And so what they said is that, okay, if you can make a squid, but you can make the left branch of the squid with aluminum and the right branch with niobium, because of some interesting Josephson physics effect, then the IV characteristic will be that of a memristor, a pinched hysteresis, which we need to represent this nonlinear resistor. And so this is called the conductance asymmetric squid, and that's eventually, further down the road, what I intend to fabricate in my lab. And so, as always, the leap from a classical superconducting memristor to a quantum one is simple because we make sure that all the characteristic frequencies are in the gigahertz range, and then below millikelvin, everything becomes immediately quantum mechanical. So we can implement a quantum mechanical memristor following the proposal by Enrique Solano and Michael Sanz's group, who actually look exactly at this part of the circuit, showing the quantum mechanical properties of this circuit. However, quoting French neurobiologist Jean-Pierre Changeux, the human brain is messy and warm. And here we're talking about experiments at low temperature, superconductivity, and high vacuum, which is the opposite of that. So at the very least, we want to introduce some local resistance, okay, to account for the local resistive channels of this device. Most importantly, what happens if we create a neural network of, let's start with 2, and then we can expand to more, of all these artificial quantum neurons with local resistance, but we connect them also with resistive channels. In fact, we can even heat them up to simulate the warmth, if you want, of the device. What happens in this case? So imagine now that in the case of synchronization, so this is connection to synchronization, we have two resonators of qubits coupled by means of a resistor, which we think will lead to entanglement. Can we do the same thing with a couple of neurons leading to entanglement? So this leads to the very last slide, which I think can help. So performing an experiment like this, which effectively is an analog quantum emulation of a dissipative neural network, I think can shed some light on fundamental questions such as, are there quantum mechanical effects such as entanglement in dissipative neural networks? Matt Fisher at UCSB, together with his collaborators in biology, they are actually thinking that it's possible in our actual brain to have quantum mechanical effects, and they have some interesting data from last year already, besides theories. In our case, it's an emulation of that, but in this age of AI, what is real and what is not, I don't think it matters too much anymore anyway, so I'm okay with that, if it's not the same. Can we build a quantum neuromorphic computer? This would be an application. There are proposals showing that we can build a non-conventional quantum computer that goes beyond quantum computing, disrupting, in fact, quantum computing, more interested in quantum computing, quantum neuromorphic computing, which could be helpful on problems such as artificial intelligence or machine learning. Let me be provocative. Can we build a quantum brain as proposed by Enrique Solano? They are proposing to implant their brains with a chip. Now, I recommend no one to implement their brain with a chip, particularly with a superconducting one, because you need to put your head in a cryostat and I think you die. But can we build a quantum brain? And lastly, let me be even more provocative. Following the steps of Sir Roger Penrose, is there quantum consciousness? Thank you.
Thank you, Dr. Matteo, for this wonderful talk. Now we have time for questions.
Thank you. So, yeah, you mentioned in one of the works how you implemented resistance in the superconducting film. What devices did you make?
So there are many different ways you can implement the resistance. The simplest one is using a thin film of gold, which we know it doesn't go superconducting to extremely low temperatures. So in the device I've shown up there, it was a thin film of gold. With this, you can make a 10 ohm resistance. If you want more, you need to develop something a little bit more complicated based on some dielectrics. And it's possible to do it, but we are beginning, small steps. So the first one is just what we know it's possible to do. Gold, or palladium if you want.
Okay, so in that case, because a resistance is basically it's a dissipative like device, a dissipative thin film, right? In that case, doesn't it tank the coherence times of the devices?
Yeah, that's a very good question. So as I said, you want each device, now the slides are gone, each device on their own, you want that to be as high quality as you want. So there we were fighting unwanted stray resistance which comes from dielectric materials we don't want there. So we want to engineer that out so that each device on their own is good. But if we put an engineered resistance, the one we fabricate, and we are actually have all the possible handle on its size and all that, in between the two resonators or qubits, that one, it does not tank the intra-resistance of this device does. That does not, and the simulation I've shown you account for that. So in the theoretical model I've shown you, that resistance is part of it. The only thing that does, it leads to synchronization. And the reason why it doesn't tank it, because when the two pendulums reach this kind of synchronous motion, there is no current through the resistance at that point. So there is a little bit of a tanking of the Q during the transient, but it's super brief. And after that, it's like it's not there anymore, because no current goes through it. I think there was, sorry, before, yeah. Doesn't work. I can bring you this.
So you answered my first question. Okay, thank you. I wanted to ask you about this coherence time. You already addressed it. So in the first part, you mentioned, okay, you removed this oxides from the silicon and you did the wet etching and you did this removal at high temperature. Did you tried it by grow the silicon and without exposing it to the environment, and you deposit the aluminum directly?
That would be a great experiment to do. Unfortunately, as you know, it's not that easy unless you have a sort of a vacuum suitcase, because as soon as you expose the silicon to air, within a few seconds, it develops its own silicon oxide native layer. So to do what you're saying, I think you need to, to clean, I don't know, actually, you can do, okay, you could do the thermal annealing, desorption, which is not chemical, because chemical in high vacuum wouldn't work, I suppose.
Yeah.
So you can do that, and then keeping the system in that vacuum, and then which is actually, we do that. So.
No, I'm saying just grow the silicon, and then on the silicon grow the aluminum. Do both of them with the growth, because you're using
Yeah. So we do that in the physical cleaning, which is what I was just explaining.
Okay.
So in the physical cleaning, we do that, right? Because we put it in an ultra vacuum chamber, we heat it up to 800 degrees Celsius, the oxygen goes away, we let it cool down, and then immediately, while in ultra vacuum, we deposit aluminum on top of it. So that's what you're saying. The chemical part, you cannot do it, because you cannot do HF deep, in ultra vacuum. it would boil.
Okay, thank you.
Yeah, I have a question about, sorry, the double well potential that you showed, and later like you proposed the thermal expansion that might be transfer the ball to the other side.
Yeah.
So we know that the energy level is no longer like KT. So how you deal with it? It's no harmonic approximation is not valid anymore for the double well potential.
So I don't completely understand. So yeah, no, you're right. It's effectively, no, I think you're totally right. Effectively, it is a classical entity. So, but the classical, like a qubit. So suppose you have a qubit, which could be represented as a double well potential, right? If you thermalize it, beneath the whole thing, there is still a double well potential. You're still allowed to use that. Now, what you're not allowed to do, you cannot distinguish between discrete states anymore. But that's not what we are doing, because at that point, we are only considering a classical event which is going up thermally above the barrier. So we are not accounting anymore for the discretized quantization of the two wells. That's completely out of the picture. It's a completely classical phenomena. I still use the double well, which is a classical feature, if you want, it's a classical double well, just to explain the problem, but I'm not accounting at all for the discretized energy states of each of the two wells. Those are gone. It's just thermal excitation allows you to go left and right. So if you want, you're right, it's a classical entity at that stage. Yeah, there was this gentleman, and then, sorry.
Yeah, you have a double oscillator for synchronization. Does it, I mean, control, increase the noise or the coherence time, or you didn't feel this, that it will add problem, or it will be solve problem in the term of noise and qubits?
Yeah, I think this question is slightly related to a previous question. So as far as I understand, what you're asking is, we are coupling two qubits with a resistor, right? And so the simulation I've shown you, so theoretically the answer is no, it should not be a problem. Now, of course, you want to make experiments, right? But theoretically, both our theory, which is independent and quite different than other theories, lead to the same result, and is that if you engineer the value of this resistance to a suitable number, this resistance does not kill the quantum mechanical phenomena. On the contrary, it generates them. It generates entanglement after the transient. And again, the reason why, just to give a sense again, that kind of works is because once you reach this mode where the pendulums are oscillating synchronously, there is no current going through that resistor, so effectively it's inactive. It's only active during the transient. So in that period, it may lead to some dissipation, but it's so short that it's not killing the final effect, okay? So perhaps it doesn't allow you to go to a super high level of entanglement, but enough to make it interesting. Yeah, so again, theoretically, also the coherence times should not be affected by this middle resistance, theoretically. Of course, as I said, we need to make these resistors with gold, which is another process on top of the process we already do. That may mess up things because of purely technical reasons, but fundamentally, the resistor itself should not. Now, other possible experimental issues, we are going to find out in the next 1 or 2 years.
Can we have one more question? Sure. Yeah. What is the characteristic time to go to synchronization? And I mean the parameters that on which it depends. And the second question is, does this affect, for example, the situation where we have multiple qubits connected together? Are they like the other qubits? Are they affected by the result of the situation of one qubit when we do it in time? When we do the readout in time?
Okay. So the first question was, how is
what is the characteristic time to go to from the transient to the synchron? Yeah.
It depends on this circuit topology we're talking about. So the circuit topology I've shown you is the easiest one pedagogically to explain, and it was two parallel LC resonators coupled in series, if you want, with this resistance. In that case, the resistance has to be a few kilo ohms because it's a sort of a parallel connection, and you know that dissipation in parallel, you want the resistance to be high to impact less, so you want a few kilo ohms. In that case, yeah, these few kilo ohms times the capacitance of the resonators leads to your...
So you have the resistance R12.
That's right. So it's R12 times the capacitance C1 or C2 of the two resonators. That's your... that's actually exactly the time constant of this problem. There are other topological configurations we are investigating which you need a low resistance to do something similar, but yeah, so it's R12 times C1 or C2. Okay. Or an average of the two if you have different C1 and C2. Whereas the second question, how these impact a bigger network, I actually don't know. So we haven't simulated that far. So I don't know how that impacts that. I have some ideas, but I don't have a clear answer at this point in time.
Thank you.
Now we welcome Dr. Mark Jackson from Quantinuum. He's one of the earliest employees at Quantinuum, and he has a PhD in theoretical physics. His advisor was Brian Greene. He's a string theorist, and now he's working on business development to find economic value in quantum circuits and quantum computing.
Thank you. Good afternoon. Is this on? This is on now? Good. So good afternoon. I'll be telling you how to build a quantum brain. No, I'm not. So thank you so much to the organizers for having me. This is actually my 4th trip to the kingdom. So thank you especially to Professor Fallenbaum for hosting me. So I'm very excited to be telling you today how Quantinuum accelerates scientific discovery and value creation. So Quantinuum is a very unique company. In case you haven't heard of us, we're only 3 years old, so I'd understand that, but we are actually the largest quantum company in the world. We were formed as the merger between Honeywell's quantum hardware team and Cambridge Quantum Computing, which was a British software startup. Each of those organizations is about 11 years old. And about 3 years ago, we merged. We now have about 600 employees. Our headquarters is in Colorado, in America. But we have a large presence in the UK. We also have offices in Tokyo, DC, soon Singapore, and New Mexico. About 3/4 of the company are researchers, of course, and this is pretty evenly split between the hardware and the software side. We're very focused on doing research, so we have about 200 scientific papers and over 100 patents. Because we do both the hardware and the software side, we really are full stack. I know that sometimes that phrase is kind of loosely thrown around in the industry, but we truly are, we truly have expertise in both areas. On the software side, we have great depth of expertise in all of these different areas: chemistry, machine learning, AI, and so forth. I'll be talking about a few of these things today. But this is a general schematic of the activities that we do. So at the top level are the applications. So these are things like cybersecurity, chemistry, AI, and then other groups of stuff. In the middle, there's a compiler, there's a operating system that we've introduced recently called Nexus, and this is very new, and this really is the first quantum operating system. It does all the things that you would expect an operating system to do, but it's specifically designed for quantum computers. And then along with that is Ticket, which is a quantum compiler that we designed to optimally execute quantum software as efficiently as possible, regardless of the platform, because often it's kind of a hassle to translate your code and run it on different platforms. And then at the bottom, there's hardware, and this could be our hardware, which I'll talk about in a moment, but it could be someone else's. So even all of the software that we develop can be run on other groups' platforms. We are really focused on developing practical applications of quantum computing. Even though we do research, our end goal is really to use quantum computing for practical industrial use. This is a small sampling of the things that we have done. And I want to emphasize these are not aspirational. These are projects that we have already completed and published, and we can talk about. You will recognize many of the names that we've collaborated with. So these are Fortune 500 companies from all around the world in many different areas. And again, I want to say these are not things that we hope to do or are works in progress. These are things that we have already completed and published. The reason that I think most of us are here today is to focus on petroleum and mining use cases. And so I want to focus a little bit more on these. These are kind of the 4 areas that this industry of petroleum and mining might be interested in, and we already have expertise in all of these areas. So these are the different collaborators that we've worked with: Total, BP, Thales, Wells Fargo, JPMC, BMW, Airbus. And so I really want to emphasize that we already are doing some of these things that different groups are interested in. Now, of course, the natural question to ask is, well, what allows us to do these things? What is different about Quantinuum compared to several other quantum companies that are in the field. A few years ago, we introduced the first quantum computer from our product called H1. So we use ion trap technology, for those of you who aren't familiar with this. So H1 was just a linear trap of a few qubits. 2 years ago, we unveiled the H2, which has this racetrack formation. And we currently have 56 qubits in this machine, and I'll say more about that in a moment. But we already have published this 5-year goal, this roadmap for the next 5 years. Our eventual goal is to get to what we call Apollo, and this will be an integrated quantum chip. And we've already signed an agreement with a German company, Infineon, to be fabricating this. Now, of course, the obvious question is, well, how do we go from the current computer, H2, to Apollo in 5 years? Before I get to that, I want to spend a little more time focusing on the H2 machine. So this is what we have right now. We've been running this for 2 years. As I said, we already have 56 fully connected qubits. This is one of the advantages of using ion trap technology, that every qubit can in principle be coupled to every other qubit, because all we have to do is shuttle it over and entangle them. Our 2-qubit fidelity, this is by far the highest in the industry. This is really the limiting factor in being able to execute quantum software, and this is by far the highest. And a lot of this has to do with just the intrinsic nature of using ion trap technology. Last year, when we did some benchmarking, for the first time, we could not replicate the results of random circuit sampling, even on a supercomputer. So we are already starting to overtake conventional computing in some of our benchmarking. This random circuit sampling, RCS, this is the same benchmarking algorithm that, for example, Google was using and has been talked about a lot with their Willow and everything. It was also 30,000 times more energy efficient. And this has been in the news a lot, how much energy consumption AI and other applications will be using. But our quantum computer is 30,000 times more efficient than the equivalent supercomputer that would be needed. Now, you may have seen last year there were some very big announcements. These were very important technical milestones in that using quantum error correction, for the first time, we could produce logical qubits. And I know at this conference there was a lot of attention given to the fact that a few months ago Google announced 1 logical qubit. We already had 12 last year, and this was done in collaboration with Microsoft. It was their quantum software team doing quantum error correction that used our hardware to do this. And this was a very important technical milestone. This resulted in an effective 800 times improvement or decrease in the error rate. And we were able to achieve 14,000 executions of a quantum circuit without having a single uncorrected error. So for the first time, this means we have reliable quantum computing. This was a major, major step. So now getting back to the roadmap, this year, in just a few months, we will be unveiling Helios. So Helios is the next upgrade. It has this kind of funny design with a circle and then sort of like a half racetrack step here. It will have 96 qubits, and it will be 1 trillion times more powerful than the H2 computer today. I'm going to say that again because this is not hyperbole. 1 trillion times more powerful than what we have today. And so we actually expect to start to see the first commercially viable applications from quantum computing by the end of this year. 2 other major announcements that we had just in the past 2 weeks. So the first is that we signed a partnership with SoftBank. So we are now SoftBank's official quantum partner, both in a business sense and in a technical sense. So we will be evaluating different business use cases with SoftBank. And in addition, we'll be setting up a research facility. So combining AI and high-performance computing along with our quantum computer in Japan. And the second major announcement was doing generative quantum AI for the first time. Obviously, AI has been in the news a tremendous amount, especially the past few weeks. And so for the first time, we're starting to do generative quantum AI. And the first 2 partners in this are with Ferrari and with Merck. And so we already have 2 major corporations signed up to do this type of work with us. Now, one thing I really want to emphasize is in Quanto. So in Quanto is it's our commercial chemistry application. This is the industry's first commercial chemistry application. In Quanto is software that you run on your laptop, and it behaves a lot like normal chemistry software. So if you're a professional chemist, you can go ahead and use this. You don't need to know anything about quantum computing in particular. You just need to be a computational chemist. In Quanto has distilled into it many, many projects that we've done. So these are just a few of the projects that we've done in chemistry. We've actually done about 50. Every time we do a project, we figure out how to do one more feature. There's one more thing that we've learned how to do. All of these features are now built into Enquanto. And so you go ahead, you just type in what you want, the type of simulations you want to do. Enquanto will do the calculations on a quantum computer and then send you the result. So again, you just use it on your laptop as you would with any other chemistry software. We're already at version 4.0. We've already had several different iterations of this, and the latest iteration, version 4.0, already includes support for NVIDIA's GPUs, because some features are optimally used for GPUs. Now, of course, the second thing that petroleum and mining might be interested in are things like machine learning and optimization, and we've already done a number of projects, including in the oil pipeline construction with Hess. And so these are things that we already have a great deal of familiarity with. So I just want to conclude by talking about our interest in working in Saudi. We're very excited about all the different use applications here. The thing that we really want to do is develop IP. One thing that distinguishes us from other quantum companies is that we don't do consulting. We don't write reports and advise groups and kind of tell them what to do and then say goodbye, good luck. We're only interested in developing applications where we build expertise and we write applications. And one thing that has distinguished us is that we either will keep or share the IP, and we will continue to grow this with our partners. And so this is what we want to do with local partners, is develop expertise in IP. We want to build Saudi into a global R&D hub. And so this includes things like sharing knowledge and developing local ecosystem development and workforce development. And obviously there is a great deal of financial gain from this. Every year McKinsey publishes a report. Last April, in their most recent report, they estimated that quantum computing's value will be in the trillions of dollars. And so we would like to be a part of that with the Saudi. So that is it. Thank you very much. Are there any questions?
Hi, thanks very much for the great talk. I had a question about the demonstration of quantum error correction on Quantinuum device. So in particular, I think the logical error rate was something like 10 to the minus 3. I also, so I haven't investigated this enough, but I think there was some discussion, some controversy about the use of post-selection in those experiments. In particular, there was some discussion on whether or not we should associate a logical error rate when the experimental method used involves essentially post-selection, which means discarding some shots where errors were detected, or the use of techniques that are not scalable. So I just wanted to know your general comment on that. And the second question I had was on the 1,000-qubit device and whether or not this will involve shuttling of ions as means, for whether it will involve the shuttling technology.
Sure. So I'll answer. So thank you very much. I'll answer the second question first. So the 1,000-qubit device, which we expect to have in 5 years. So this is on, again, this is on an integrated chip. Everything's sealed, self-contained, room temperature, and everything. So it should, I believe it's 1,000 logical qubits. So it should be several times more than that even for physical qubits. So yes, they would be moving around with integrated photonics and such. The first question, I do vaguely remember something about post-selection, but I don't. Yeah, I actually can't comment further. I vaguely remember hearing something about that, but yeah.
Yeah, it is extremely interesting, nevertheless. So whether or not there's post-selection involved, it is a really interesting result. So thank you very much.
Thank you very much. For the interest of time, we'll move to the next presentation. We have Dr. Junaid Al-Rahman. And we'll skip the break, by the way, because we are running behind schedule. So Dr. Junaid Al-Rahman is a quantum communication and quantum information expert, and he's a professor at KFUPM Electrical Engineering Department. Please help me welcome him. Thank you.
That's not me. please do not open it in the Google Chrome. Please open it in Adobe Acrobat. You have opened it in Google Chrome. There are some animations that I do not want to miss. There. Perfect, thank you. You can press Control L for the full screen. Control L. Okay, perfect. Thank you very much. Good afternoon, everyone. For a change of flavor, I'm going to talk about quantum communications instead of quantum computing. And this talk relies on the fact that now you are all convinced that quantum computing is coming. Okay, so in next few years, depending on who you talk to, if you talk to the industry experts, they will say you open this door, quantum computer is outside. If you talk to academics, they say it will take some time. So there is some discrepancy between the opinion, but eventually the quantum computer will be here. And this is what the quantum communications, the biggest application of quantum communications takes its motivation from. Okay, so in this talk, I'm going to talk, there are three main something like topics in my talk or themes in my talk. So I will start talking about quantum key distribution. This is kind of historical knowledge, background knowledge base. Then we will talk about quantum key distribution networks. In this one, we are going to talk about the activities that are going on at the moment around the globe. And then we will talk a little bit about quantum internet. We will see some moving components or some of the components of quantum internet. So that is something that is in far future. Okay, so the motivation for the quantum key distribution, or which is the biggest application of quantum communications, is that if you have a large enough quantum computer, it is possible to break your public key cryptography. So the public key cryptography, the RSA algorithm, for example, is what is securing your banking transactions, what is securing your emails, everything. So the consensus is that there will be a quantum computer, but we do not know when. So in order to make get a little bit better than just guessing or making your own opinion, we can talk. We can ask from multiple experts, and based on their opinions, we can form a kind of aggregated estimate on when the quantum computers will be available. Okay, so this is opinion-based estimates of availability of cryptographically relevant quantum computers. So the quantum computers that are big enough to break your cryptography. And the source of this is Quantum Threat Timeline Report. This is a report that is published everywhere, every year. And based on this, we can see that, okay, within the next 5 years, the chances that we will have a cryptographically relevant quantum computer, these are quite low. But as we look further into the time horizon, we see that there is a very big chance that in 30 years, maybe, even the most pessimist people, the experts, they consider that there is a 77% chance that we will have such a large quantum computer. Okay, so further moving into the same discussion, that we now understand, okay, after some couple of years, your encryption of your data will be at risk. So the question is, should you start worrying right now, or there is some time for you? So the answer to this is in this theorem, the Moscow's theorem. The basic idea is that every secret has a shelf life. Okay, if it is your banking transaction, the shelf life is not very large. But if it is some governmental secret or military secret, there is a chance that the shelf life of this secret is 20 years, 25 years, or 30 years. Then we have the migration time from your current security systems, for example, from RSA to something next. In our context, we are going to talk about QKD. So this is your migration time. And then you have the threat timeline. In the motivation that I'm taking from quantum computing, so the threat timeline is the amount of time that it requires for a large quantum computer to be built. Okay, so we do not know the answer to the Z, but we know we can roughly have some idea about X and Y. So if this X plus Y is greater than Z, it means that there will be some time in the future where you do not want your secret to be out, but it will be out because of the availability of large enough quantum computer or some other kind of algorithm or protocols. Okay, so this is when you should start worrying. The weakness of RSA cryptography or some other cryptography algorithm comes from the specific paradigm in which they operate. So these algorithms, they operate in the paradigm that you pick a very computationally difficult problem, and then you say that it cannot be solved, and you build your whole cryptography system around that problem. So, if, for example, the Shor's factoring algorithm, we know that it is possible to factor out the large numbers into their factors. So the RSA is broken because of this assumption that it was impossible. The other alternative is something called the information theoretic security. This is not something new. This is coming from Claude Shannon. He came out with the first conditions on how you can build an information theoretically secure system. The good thing about this encryption paradigm is that you do not need to make any assumption about the computational power of your adversary. Okay, so example of that is one-time pad. The one-time pad or for information theoretically secure systems, you need certain conditions on the key. So the challenge here is that your key length, the key is something that you are using to randomize your message or something. So the key length should be as large as your data. So for example, if you want to share let's say a video file of 5 GB, you need a 5 GB of key as well, okay? And then there are some technical conditions. It should be truly random, it should remain secret and never be reused. So with this set of conditions, we see that the one-time pad itself is not very difficult. Computationally, it is just excluding OR of your message bits with the key bits. So it is not difficult, but sharing the key is difficult. So that is the challenge. If you already had some secure communication channel, you could share the key on that, but we are going with the assumption that you do not have a secure communication channel. So in this with this context, there are two very relevant concepts in quantum mechanics. The one is the uncertainty principle. The idea is, most of you have this idea, but let me just say a few words on that. The uncertainty principle, the idea is there are multiple properties of your quantum system, and some of these systems cannot be measured or cannot be defined simultaneously. Okay, so the example is position and momentum. If you define the position of your quantum particle, the momentum is randomized. It is completely uniform random. So the idea that we use in quantum key distribution of this is that we encode our information in these pair of conjugate variables. We sometimes use the first variable, other times we use the second variable, so that they are not well defined in both of them simultaneously. And then we do some kind of post-processing, some discussion between the communicating parties. Based on that, we can distill the key. The second important principle is the no cloning theorem. So if no cloning theorem were not true, it would be possible for an adversary to copy your ongoing qubits, and then afterwards, when there is public communication, come out to understand, okay, which variable the key was encoded in, and then use measurement in that to measure that specific variable. So these two principles together give rise to something what we call quantum key distribution. Okay, so quantum key distribution is not an encryption algorithm in itself. It is just a means to share secret, randomized secret bits. And then you use these bits to encrypt your message. So that is the very simple principle of quantum key distribution. And the first protocol for quantum key distribution came actually in 1984. Okay, and after this quantum key distribution, theoretically, okay, we know everything, but there is a saying that in theory, the theory and practice is the same, but in practice, it is not. Okay, so in practice, when you go on and try to implement this theoretical understanding of how the quantum key distribution should work, you come into practical challenges. For example, one of the challenge that I write it here because of its importance, but it has already been solved, is that quantum key distribution relies on the fact that you have single photon lasers. Okay, you have lasers that can emit single photon at a time. But if you are working with quantum key distribution, we are relying on no cloning. But if your source is emitting 2 photons, we are already generating clones of what you try to send. Okay, so the solution to that was the decoy state method. So instead of you do not have a single photon source, but you generate multi-photon sources intentionally, and then based on difference in statistics of your pulses, you can infer if someone is trying to steal your photons. The second challenge is the small achievable distance. So there is a fundamental limit on how far you can communicate with in quantum communication. So this fundamental limit is around 150 to 200 kilometers, depending on how good your sources are and how good your channel is. If you want to communicate beyond that, there are there are three solutions. One is there are 2 solutions that are near term. By near term, I mean that they have been demonstrated and they are working today. One of the solution is the satellite-based quantum key distribution. The other one is to include trusted repeaters. Okay, so if you want to communicate to 400 kilometers, you put a trusted node in between at 200 kilometers. You tell your secret to the 200 kilometers, and this 200 gives. So this is trusted node-based solution, and this is not a very good approach. The second approach that is working today nowadays is the satellite-based quantum key distribution. We will have a little bit of discussion on that. And then the third and the last challenge here, not the last, one of the last that I have mentioned here is the small key exchange rates. The key exchange rates of quantum key distribution, the commercial devices that are available are only in few kilobits per second. So less than, most of them are less than 10 kilobits per second. So this is, so in order to ask, okay, the satellites are working today, but are they going to be necessary when we have quantum repeaters? There is some specific device. Currently they are not very practical. Mostly it is theoretical, but we have some variants of quantum repeaters. But the question is, when we have big enough or more very reliable quantum repeaters, are we still going to require quantum satellites? This is the question that I'm posing here, and then we can see a configuration without any repeater at all. There is Alice and Bob that want to communicate, and there is a source in between the two, Charlie, which is generating entanglement between Alice and Bob. This is the first configuration we are going to look at. The second configuration is that the Alice and Bob each is connected to some optical ground station, respective optical ground stations, and these ground stations, they are connected by a satellite. Okay, in this study, we are considering just a LEO satellite at 500 kilometers. And the last configuration I'm considering is with quantum repeaters. There is a source here that is generating the entanglement between the two end nodes, and then each of the end node of each section are connected with each other, and they are performing something called entanglement swapping. The entanglement swapping is a concept that if you want to generate entanglement between this node, Alice, and this node here, then you can generate entanglement with the node that is in the center, and then the central node can perform some measurement, and as a result of this measurement, all of the end nodes, they will share an entanglement. Okay, so this is the concept of entanglement swapping. So this is the question we posed, and then we did some simulation. This pair is very obvious. If we have just the fiber-based APR pair sharing, the red line here, without any quantum repeater at all, and the blue line, the satellite-based EPR pair sharing. So this is a very trivial result. Obviously, this will be very much limited because of the fundamental bound. So this is not the interesting case, but the interesting case is this one. So the black line here is the EPR sharing rate when we are communicating through a satellite, and these red, blue, and green lines, these are when we have the repeater sections that I shown you in the previous slide. And why we have this kind of result is because of the entanglement swapping process, the coupling of different nodes with fibers, and these all lead to the the losses and the noise. So because of that, if you have, for example, 100 a repeater chain of 100 repeaters, each repeater will introduce its own losses and noise. So it appears that even when we have quantum repeaters that work quite well, if we want to communicate globally, the satellites are going to be absolutely necessary. Okay, so before concluding this part of the my talk, I just want to mention that QKD is not the only solution for the quantum secure cryptography. We have something called the post-quantum cryptography as well. These post-quantum cryptography algorithms, these are classical algorithms. These are not quantum algorithms, but they operate under the same paradigm of the computationally secure cryptography. They are built on the problems that are challenging even for quantum computers. Okay, so this is the only difference. And then there are some security agencies all around the globe. They have their own opinions on that. Some recommend using quantum key distribution. Most of them not recommend using quantum key distribution. And then there are, for example, the NSA published a report where they provided specific critique on quantum key distribution. One of them is quantum key distribution increases the risk of denial of service. Another challenge that is not mentioned here is that the QKD is a point-to-point technology. It is not a network technology. Okay, so in order to address some of these comments, for example, the denial of service or the point-to-point technology, we need to build quantum networks. Okay, so the denial of service, if we have many redundant routes between two nodes, the denial of service is more challenging as compared to if we have only a single path. So we are going to look at what is the activity going on quantum key distribution networks around the globe. So this is a map that I have picked from this very nice survey from Professor Hanzo. So here you can see that the quantum key distribution networks are being built around the globe. We see a lot of activity in China and in Europe. And China is also very successful here in these networks, especially if you look at the next slide here. For example, you see this China-Austria link. This link was 7,600 kilometers, and this was the first satellite-relayed intercontinental quantum key distribution. And this experiment was in, I think, 2017 or 2018. Okay, so this is not something new. And another very prominent activity that is going on at the moment is the EuroQCI, the project called EuroQCI. The idea of the EuroQCI is all 27 European Union member states. They build their own national quantum communication infrastructure, so quantum key distribution network with 5 nodes, 10 nodes, 20 nodes, whatever the number. And then eventually this will be connected throughout the Europe. So there will be at the end a Europe-wide quantum key distribution network, which will be supported by the Eagle 1 satellite. Okay, so this is the second activity that is going on at the moment. The planning, the network planning, so I will just skip through these slides. So this is one of my work that I did with my collaborators. So in this one, we were just looking to minimize the cost of QCI development. So by looking at the structure, the topology of the existing networks, we try to come up with a quantum communication infrastructure topology such that the cost, the expenditure, or the dollars is minimized. And we found that, okay, it is possible to reduce the number of the amount of money that you have spent on this one. But with that, we also have some side good effects, not the bad effects, that you can reduce the power consumption, and you can also reduce the number of trusted nodes in your network, because the trusted nodes also cost you money. The power consumption also means that if you have many devices, the power consumption will be larger. So once you try to minimize the cost, you also end up reducing some of the other things that you want to reduce. Just last parts very quickly. We are in the present day and near future, we are looking at the quantum key distribution networks augmented by classical orchestration and key sharing. In the intermediate steps and the far future, we are going to look at the further applications of quantum communications. There are many applications available. The long-term goal is the quantum internet. This quantum internet will be built, will take motivation from the networks of today. For example, I unfortunately missed the talk this morning about the network quantum sensors, but that today's all the quantum networks operate in a single layer of this. So either they are quantum key distribution networks, or they are computing networks, or the network of sensors. The quantum internet is going to be a combination of all three, and the scale is also going to be very large. So if you want to look at the different stages of the quantum internet, we are something called the first generation of network. And if we want to go beyond that, the first generation, you need to generate the ability to for entanglement generation. And entanglement generation has 2 steps. One is just the distribution of qubits. But because of the distribution, there are some channel noise which reduces your amount of entanglement. The second step is the distillation or the purification of entanglement, which operates on multiple pairs and then generate something stronger with stronger entanglement. So this gives you rate fidelity trade-off on a link, okay? And this was only on single link, but if you go to a network, the rate fidelity curve becomes very, very complicated, and solving the routing problem in quantum network with specific fidelity or specific rate guarantees becomes really challenging. And in this work, we are working with reinforcement learning for the optimization in quantum networks for entanglement generation. And we can make our reinforcement learning algorithm to operate in 3 different modes: the rate priority, the fidelity priority, or the balanced mode. And then based on that, we can actually, if we give the rate the priority, we can generate entanglement with higher priority. If we give the fidelity to the priority, to the fidelity, we can generate with higher fidelity. Just the final slide of the conclusions. Quantum communication has seen rapid development in the last decade. Commercial quantum key distribution devices are available today. There are problems with that as well, but let's discuss about it later, offline maybe. Today's quantum computers are mostly functional, meaning that they are dedicated to a single task. And the satellites remain an essential component of global scale quantum networks, possibly even in the presence of quantum repeaters. So here are some further readings if you want to dive into this wonderful field of quantum communications. And here are some software that can be useful both in quantum computing and quantum communications. Thank you very much.
Thank you, Dr. Junaid Rahman, for this wonderful talk. For the interest of time, we'll skip the questions, and please have questions with him offline after. This is our last speaker before the panel discussion after him. Dr. Hermani, he's from IQM in Finland. I guess IQM is International Quantum Machines. Dr. Hermani is a theoretical physicist by training, and now he's the head of product at IQM, but he's still involved in quantum computing research. Thank you.
Thank you for the introduction. In order not to spread fake news or anything like that, as far as I know, International Quantum Machines is not the explanation for the name. And I think Mark is the only person in the room who can actually tell us what it means. It is a bit of a mystery. Yes, so first of all, thank you. I want to thank Mahmoud. I want to thank everybody here for organizing this conference. It's been a really great conference, really a lot of diverse points of view on the quantum computing field. I've learned a lot personally. Even my PhD was in quantum synchronization, so it was a delight to see that here today. Now, I'm going to be bringing one more point of view on the quantum computing field. And the title of my talk is Quantum Computing the IQM Way, an open and transparent research platform. And I want to kind of dig into this and see what we mean by that. And I'll start by talking about the company mission. These are often things you find in the corporate website somewhere, and people forget about them. But I think this is really guiding what we are doing at IQM. So our mission is to build world-leading quantum computers for the well-being of humankind, now and for the future. Now, yes, this absolutely sounds like corporate speak, and it is. But let's dig into this a little bit. It starts with we build. Now, this is really at the in the DNA of this company. We build quantum computers. This is at the core. World leading refers to the quality, also refers to the usability, and is a kind of a very broad term for us. Well-being of humankind refers to the algorithms and the use cases we are working on. We'll get to those in a bit. And then there's a now and for the future part. Quantum computing for a long time has been the future. We have seen many presentations where we start from 30, 40 years ago and project to when we heard about the path to quantum advantage yesterday. But there really is a now angle to quantum computing as well. In fact, I believe this conference is because of that, realizing that things are happening fast now. And this is the time to build IP, to develop the workforce, and to do all those preparatory things in order to leapfrog your economy, just like the university president told us at lunch today. So this is at the core of what we do. So who are we? What are we? So we're a company, as I said, we build quantum computers. We were founded in 2018. The company properly got started at the end of 2019 when we got our seed funding. Today we are 280 employees, so a little bit behind Mark's company here, but we're catching up. Also, more than half of us have PhDs, and I think probably the vast majority of the rest have masters as well. So we are very research heavy. This is a research heavy field that shows up with all these companies, of course. We are from all over the world, from 45 countries at least. There's a plus because, well, we're probably recruiting someone from a new country as we speak. And all of this, of course, takes money. So we have collected over 200 million euros in funding to date. That number has been the same for about 2 years. I can tell you there's going to be an update to that soon. You should hear some news about that very soon. But I think the thing I want to focus on is on the left there, that we have built over 30 full quantum computing systems to date. And 7 of those are at customers right now as research platforms on customer sites, training students, building IP, right? And it says 7+ because there's at least 3 of those that are being delivered right now at the same time. And you'll hear some announcements about some new sales cases soon as well. So this is really what I want to stress, that this is a technology for today that is available. Some of them are off the shelf. Some of them are more forward-looking. But it is really something that we have seen that has sprung up quantum ecosystems in countries across the world. So here we have our offices, our locations where we have staff across the globe. Our headquarters is in Espoo in Finland. It shows that Espoo is in the far north of Finland. It is not, and is in the far south. And then we have, so this is where we have about 150, 160 of our staff. Then there's a large office of about 70 people in Munich, in Germany. That's a large R&D center there. And then we have smaller offices around the world with a little bit of R&D and a lot of business development. This map is highly correlated with the next map. This is the map of our customers. We have customers in Finland, Germany, Italy, France, Czech Republic, United States, Taiwan, South Korea. These are institutes with an IQM quantum computer. Here is a list of the products we have signed with these customers. We'll get to the product details in a little bit. We have Spark, which is the entry-level offering, a 5-qubit quantum computer. And then we have IQM Radiance, which is the larger quantum computer, an upgradable system that you can upgrade from 20 qubits all the way up to 150 qubits. And these have, you can see these are the systems the customers have bought. Some of these have not been delivered yet. I think two or three of them have not been delivered yet. VTT is our first customer in Finland. We signed a contract with them in 2020. I think that was about 2 weeks after I joined the company at the end of 2020. And we have just completed our delivery of the first 54-qubit system to VTT. Official announcement is coming in a few weeks. And this is really, in Finland, the VTT purchase was really the nucleation point for quantum computing, the quantum computing ecosystem and the economy springing up. This was at the end of 2020, and there was IQM, and we were the only quantum company around. VTT got some national funding. VTT is a national lab in Finland. They got a little bit of funding to buy quantum computers. Today, we have 10 quantum companies in the country. So we have really seen that this showed that there is investment, there is interest in the field, there is, and there's a will to invest into this field. And we have really seen this ecosystem spring up around us, and many foreign companies have invested as well. We've seen the same thing in Germany at the Leibniz Supercomputing Center. This is what David talked about yesterday. In this summer, we delivered the Radiance 20 system to LRZ, and this is the world's first HPC integrated quantum computer. We'll have a look at that in a bit. This was coming from a large investment in Germany into quantum computing in 2021, 2022, and same thing there. We're now seeing that there's a strong and robust quantum ecosystem in the Munich region. Of course, this is a big effort. We cannot do everything ourselves. We're only 300 people. It is one of the biggest quantum computing companies out there, but still only 300 people. So we, of course, do this with a lot of partners. I've been glad to hear talks from many partners here. Our system, IQM Garnet, is available on AWS. They're up there. We have a research collaboration with Berkeley, with Erfan's group. It's wonderful to see him here. And you see many, and then we have our customers who we also learn from and do research together with. So here I have the storyline of what happened with the Leibniz Supercomputing Center, LRZ, in Munich. At the end of 2021, IQM was selected to provide a quantum computer to be integrated into an HPC supercomputer. Then we did research, we did the contracts, we had a lot of back and forth. There's a public institution in Europe, takes time sometimes. Finally, in June 2024, we delivered the system. It is sitting there in the same building, in the same room with the supercomputer. And this is, we believe, the world's first full integration of a quantum computer into a supercomputer. And now we are seeing papers coming out from this where people are really researching both the software. How do you develop the software that connects the two and does this coordination, what David spoke about? But also, what are the interesting applications when you have access to both resources? So we've already seen some talks at the supercomputing conferences, and we're expecting to see now the papers coming out from LRZ's customers. It's LRZ's machine. LRZ is now giving out access to researchers they choose. Now in October, we were then selected to deliver 2 more systems to LRZ, a 54-qubit system and a 150-qubit system. The 54-qubit system being delivered this summer. 150-qubit system is being delivered next year. And I think Marcus Blum's statement here really summarizes what we're talking about. He's the Bavarian State Minister for Science and the Arts, and he said that this is an international breakthrough and strengthens Bavaria's position as a global hotspot for one of the defining technologies of the 21st century. What we're really seeing here as well is that this is acting as a nucleation point. Having a quantum computer in Munich at the premier supercomputing center owned by the universities. This is where students on campus can come and see the quantum computer. And the psychological shift between teaching a class that says that, yes, we will program on a cloud quantum computer, and saying, there's the quantum computer, and you will be programming on that. There's a big difference in the mindset and how interesting that is, that class is. This is really what we're seeing is this nucleation point, that this is putting things in gear and moving things forward. And now we're seeing that this is a model that resonates. So I took here one of our slides of latest highlights from the marketing deck. And what I really want to highlight is this picture here. At the end of last year, in November and December, we had 2 more sales cases of IQM Spark. First to the Taiwan Semiconductor Research Institute, and then to Chongbuk National University in South Korea. We're now seeing that there are forward-looking universities that are seeing that this is the time to act. They are seeing that quantum computing will be a big part of the future economy, and they want to get on that train. And we're now seeing a lot of countries investing into this in order to jumpstart their quantum economies as well. So let's look at what's behind the engine. What's happening at IQM? How do we make this happen? What's going on? Right, so this first part was the marketing part, the value proposition, and now let's look at what's behind. So here, this slide describes quite well the activities we do at IQM. We have design and fabrication of the QPUs, of the chips. So we build superconducting quantum computers. So you have seen now many talks about with pictures of the components and electrical circuits and all of this, so I will skip that. But we have design tools. Actually, some of those are open sourced, and we have some educational content for designing QPUs as well. The software is called KQ circuits, based on classical K layouts, PCB layout software. So we design the chips and we fabricate them. We integrate the full system. So we take the fridge, we put the chip in there, we manufacture the electronics, we connect the package, we do all the shielding, ensure the quality. We build the software, so we have the complete control software stack. Also with HPC integration modules and cloud interface. So we have IQM Resonance, our own cloud. We'll look at that in a bit, but this is also something that can be installed on the on-premises quantum computer. And you can use this cloud interface to share the computing resource to your users. And then finally, we have the algorithm, error mitigation, and error correction teams that are working on the use cases, that are working on the ways of using the quantum computer, and IQM quantum computers in particular, in a clever way. And this then gives us feedback at the beginning. How should we improve our quantum computers? How should we improve the design and the fabrication? And round and round and round we go. Now, before we look at why that's quite fast, I want to look at the software stack a little bit more in detail. We've heard a couple things about similar things here already yesterday and today. So the software is available for the on-premise and the cloud systems, yes. But then we have this open platform. So the thing we have here today is that we have a free choice of tools. We support most of the well-known programming frameworks. There's Qiskit, there's Eshtrk, there's Captiva, or from Eviden, or MyQLM, I believe it's called. I think they corrected me today. There's CUDA, there's Classic, there's TCAT from Continuum. All of these are supported by the IQM backend. Some of them are bigger, and some of them are smaller projects, so they might have more or less features. But whatever you are using, we are already supporting that. We also don't do tricks in the backend. We don't do things, we don't move the qubits around, we don't perform funny operations without telling you. When you send us a circuit, that's what we execute. We will give you options from the algorithms and applications packages later on, where you can apply different methods. You can apply error mitigation methods, dynamical decoupling methods, and the likes, but in a transparent manner. You know what you're doing. You want to have, yesterday we had a talk by David where he was talking about these 3 R's, repeatability, reproducibility, and forget the 3rd R. But this is very important for us. We are building scientific equipment for doing scientific experiments and building IP and know-how. We want to make sure that the experiments are repeatable. One more thing to mention about the software stack is that we also have their automatic calibration. System is, we deliver the system, we do the first calibration of the system by hand, then we let the automatic calibration procedure run. There's no human intervention required. Every 6 months, there's a small maintenance operation for the fridge. Otherwise, system calibrates itself. You can choose when you want to do the calibration so that it doesn't interfere with your experiments. And you can choose how often you want to do that, depending on how tightly you want to control your calibration. Again, open and transparent. You have full control. And then we are developing HPC integration middleware deployability. This is something I will mention in about 5 minutes, a little bit more about. So then the other parts of that cycle for us is quite fast and has been speeding up since 2022 when we got our own fabrication facility. This is one of, I believe, 3 privately owned quantum fabrication facilities in the world. Here, what we learned, we were using the VTT clean room in the beginning, and then we found some graduate students put the plastic tweezers in the wrong machine, and now the machine is out of use for 4 months, while VTT is replacing that or getting it maintained. And company, when you stop for 4 months, that costs a lot of money. So we invested into our own clean room where we can control all the parameters. We can get all the best equipment we want and start bringing in expertise from the semiconductor industry on how do you run a fab, how do you collect data and optimize the fab. So now in this new fab of ours, we have demonstrated 99.9% 2-qubit gate fidelity on 2-qubit samples, and we have demonstrated 1 millisecond coherence times on test qubits. These are test qubits that have been designed specifically for long coherence time, not for fidelity. But these are both state-of-the-art numbers. These are both as good as any fab out there. And we now know that we are in a position to start taking the next steps to go beyond what exists today. And this has really accelerated our design and production cycle by about 10 times. So where that's gotten us now, today, since 2019, so in the last 5.5 years, is that we have the world's largest assembly line designed to deliver on-premises quantum computers. And today we have the capacity to build 20 full-stack quantum computers a year and deliver these either to ourselves for R&D, to our cloud, or to customers who are interested in building their own quantum ecosystems. But of course, this is not enough. We're not going to stop there. We see that this field is picking up very fast, and we see that the requirements for the fabrication are also increasing. Oh, sorry, I say taking a picture if you want. I can go back. Oh, got it, good. So we are now investing into our future, into the future fabrication facilities. And we have announced that we will be opening up a new fab in France, where we'll be moving to a larger wafer size to get access to more advanced fabrication fabrication tools and processes, and to be able to scale our production significantly. So what comes out from the fab? We make two types of chips. We have IQM Crystal and IQM Star. These are the two topologies of the QPUs we manufacture. Right now, IQM Star is only available on the cloud, while IQM Crystal is available on the cloud and on premises. IQM Crystal is a square grid. It says here standard square lattice QPU topology. This is a little bit boring to say since this is the highest superconducting qubit connectivity in the market. Nevertheless, it's relatively standard, and this is with the surface code in mind. Here on the 20 qubit system, you can run a surface code distance 3. On 54 qubits, you can run surface code distance 5 experiments. Then we have Star, which is a number of qubits connected to a central computational resonator. We just learned about resonators and qubits in a couple of lectures today, so I won't go into that. But effectively, what this gives us is global connectivity. With the right protocols, you can do all-to-all gate connectivity, or if you want, you can do hybrid gates between the qubits and resonators. And now you are in the Jaynes-Cummings world. You can do so-called Jaynes-Cummings gates. We have a tutorial on our IQM Academy on how to do Jaynes-Cummings gates. So gates between a qubit and a resonator with many high levels. And there's a very exciting research paper coming out about that from our partner HQS. HQS in Germany, a software company that is looking at simulating open quantum systems. Here we have some of the specs for our 20 qubit system. This is IQM Garnet, the device that we have on our cloud, on Resonance, and also on the AWS Brockhead service. We have same qubit counts, fidelities. The two benchmarks that I find kind of interesting here is the G8Z genuinely entangled state. So we can show that we can entangle all the 20 qubits in a genuinely entangled many-body state. So that's kind of an interesting one, at least for me as a theoretical physicist, foundational physics PhD. This is kind of an interesting one. And then we have the Q-score, which is the size of a larger size of an optimization, a combinatorial optimization problem you can solve on this. This is a benchmark defined actually by Eviden. Our friends at Eviden has defined this on dense graphs. And this is really the most application-oriented benchmark that I know of, at least. So this is an interesting one I recommend having a look at. So I've mentioned product names. Let's have a quick look at the products. First product, IQM Spark. Right? There's a long list of Sparks sold on the previous slide there. So IQM Spark, here's a picture of it. Actually on the screen, it's, well, it's not quite real life. Real life size is more or less the size of the screen itself, a little bit smaller. And this is a 5-qubit quantum computer. This comes with all the components of a superconducting quantum computer. It's very fast delivery. You can get one in 6 months from signing the contract. And you will get all the parts of a superconducting quantum computer, including the control software, the electronics, the wiring, the fridge, the chip. You can take it apart. You can reassemble it. You can do as you please with this. If you are starting a new research group that is building is interested in superconductivity, your PhD students don't need to spend the first 4 years of their life building the system. Instead, you get this in 6 months, and now you put in that component that you wish to research, because we have certified that the system works. Now I will not say quote a price for Saudi Arabia. I am not sure about the taxes here. In Europe, we sell this for less than 1 million euros. So I guess that's around 4 million real. Then we have IQM Radiance. IQM Radiance is really the quantum computing platform. With 5 qubits, you're very limited in the algorithms you can execute. So it is for education, it is for research. It is wonderful for that. But for algorithms, for error mitigation, we need to scale the number of qubits. So this is where we get IQM Radiance. It is designed to be in an HPC center compatible form factor. So the shape of that is this long rack. And it is the width of an HPC center. So you can put it in an HPC center, but you can also turn it around. We can twist it. We can modify it to modular shape so we can make that fit your room. This comes with 20, 54, or 150 qubits. And it's an upgradable system. You can buy in at any level and keep upgrading the system without additional cost from the new cryostats. We then have IQM Resonance. This is our cloud platform. Here you have, I'm missing the slides with the processors, but this is where you can book slots for yourself. You can use it either on demand, pay as you go, or you can book slots and have dedicated access so that only you are using the quantum computer. On Resonance, we will have Crystal 54. So the 54 qubit system that is also in Radiance, that same chip, will be available in Q1, so probably in roughly 1 month. It might slip by a few days into Q2, but this is coming soon. And finally, I want to mention IQM Academy, which is your one-stop shop for online quantum education. I've spoken to some of you about this already. The address is here. Unfortunately, there's no QR code right now, but it's iqmacademy.com or academy.meetiqm.com. And this is a way to start learning quantum computing. If you're interested in hardware aspects, in algorithm aspects, software aspects, we have tutorials on all of these designed by a real educator. Very nice interactive tutorials. Now I was shown I have 1 minute, so I will flash our development roadmap here. Let's not go deep into that, but I will just want to highlight things from the software platform. That in 2024, we have demonstrated so-called loose HPC integration. This is what we did with LRZ. This is the state of the art in the field. We are now in about 2 months releasing the first HPC integration guidebook. So we're taking the lessons we have learned with our partners, with our customers, and we are publishing those as high impact research, but also as a guidebook to share with the world. This is how you integrate a quantum computer with a supercomputer, the lessons learned. And this is then taking us towards tight HPC integration that I'll be happy to answer questions about. Also, I mentioned this open and transparent platform. The openness has started definitely last year with this pulse level access that is now available to all of our on-premises customers, also coming on the cloud in a limited fashion. And this is going to evolve into an open architecture and programming framework with lots of APIs, standardized APIs you can connect to and start building your own IP on top of. Then I will just leave it here and say thank you very much.
Thank you, Dr. Hermani, for this wonderful talk. In the interest of time, I was told not to have questions. We'll have the closing ceremony now in the presence of our beloved Vice President for Research and Development, Dr. Ali, who will come here in a few minutes.
So good afternoon, everyone. I know everyone is tired. Thank you so much for sticking around. Over the past 2 days, we have very successful sessions. We have heard very insightful talks. Thank you for each one of the speakers for attending with us today. We had a lot of interesting talks, side talks as well. Thank you for the students who submitted their posters. To me, and I heard this also from many of you, this was a very successful event. And I contribute this not to myself, but also to the whole group at KFUPM in the center, KICS, and everyone else. So first of all, thank you. And I would like to thank the organization or the organizing group as well. So allow me to invite to the stage Dr. Ali Al-Sheikhi, Vice President of Research and Innovation, to give the concluding remarks.
Thank you very much, Dr. Muhammad. I was not expected really to say anything. I just felt sorry for the guy. I was, by the way, watching on YouTube. They were saying, no questions, we will start the closing ceremony. Beloved Vice Presidency. So I was running, coming from there, I was not here. But anyway, I reiterate what Dr. Muhammad Filimban mentioned about this successful symposium. Thanks and appreciation for all of those who really participated in it, in organizing this event. And there was lots of preparation. And all the committees, the other also subcommittees, as I mentioned also in my opening, thanking all the university administration for making this symposium. Special thanks also to Dr. Muhammad Filimban and his center for organizing the event. KICS also, and also the company, they did also fantastic job. I know that the first day it was a bit hectic because they had some issues, but I think they did after that fantastic job. I'm really pleased that KFUPM is organizing this futuristic type of symposium because it's about new technology. And I always say that all technology definitely needs, always you need to partner, to work together. Just imagine if we are talking about something new that we don't know even what will be the future of this technology like quantum. So, so definitely it's our collaboration and partnership that will drive maybe the boundaries more and more in this new field of technology. So the organizing of this event is by itself was an objective to really see all the people coming around the world. So I also thank the speakers for sharing all their views. We hope that we will even reflect more about whatever we did here and even try to help each other and work together in this field. So don't want to take much of your time, but I would say that quantum computing, even if you combine it with other technology like AI, will have maybe endless applications, and it may revolutionize the future of our community. So all what I'm trying to say is quantum computing is not about what it can do for us, but what we can do with quantum computing for the betterment of our society. Thank you very much, and I hope you can organize this event in the future, and we have even much and more and bigger event, inshallah. I say thank you, but by the way, the kingdom in general, they are really lots of resources now in quantum computing. We are partnered with even the Research, Development and Innovation Authority of the whole kingdom in quantum computing. We are hiring here with chair professors, faculty member. We are investing a lot actually in quantum computing. We are building our quantum computing facility as we speak. We hope it will be up and running soon. So I think the future is great and bright. Thank you very much. Assalamu alaikum wa rahmatullah.
Thank you, Dr. Ali Sheikhi, for your closing remarks. We'd like to ask you to stay on stage for the awarding ceremony. Okay. We'd like to first reward our strategic partner, RDIA, represented by Dr. Fahad Al-Zahrani. We'd like to award our speakers. Would Professor Matteo Mariantoni come to stage? Let's welcome Professor Jacob Cunningham to stage. Would Dr. Salim Rao come to stage? Now we'd like to welcome Dr. Hammam Qasim to stage. Please welcome Mr. Julian Maliarts to stage. Please welcome Ms. Rawan Araqi to stage. We'd like to welcome Mr. Muhammad Al-Sayyari to stage. Please welcome Zia Muhammad to stage. Let's welcome Dr. Mark Jackson to stage. We'd like to welcome Professor Junaid Al-Rahman to stage. Please welcome Dr. Hermani Haimoune to stage. Would Mr. Muhammad Ayyash come to stage? Please welcome Mr. Rayyan Muhammad to stage. We would like to award the following individuals who are absent. Professor Arfan Siddiqui. Dr. Muhammad Al-Sharif. Dr. Hussein Al-Salim. Now we'd like to award our community. First with Dr. Muhammad Firimba. We'd like to award Dr. Abdul Wahab Al-Haydi. Please welcome Dr. Abdulaziz Al-Tabbakh to stage. We'd like to welcome Dr. Burhan Saifuddin to stage. Please welcome Engineer Shroq Al-Agibi to stage. We'd like to award the absent Dr. Abdullah Sultan. Thank you all. It has been a wonderful symposium. This is the end of our symposium for today.